We can measure the mass of a single electron to 12 decimal places, yet when we ask how many universes exist, the honest answer sits somewhere between 1 and a number too large for every book on Earth to hold. Tonight, we are going to run that count anyway, one careful step at a time. We will start with the atoms inside your own body. Climb to a number so large, its digit count has more digits than the universe has particles. And then watch the counting itself break in a place no one expected. If these quiet science stories have ever kept you company on a sleepless night, a gentle like or a soft subscribe means more than you know. It keeps this little universe of ours alive and tells me that somewhere out there, someone is listening. Now, close your eyes and follow me. Start with a question that sounds like it should already be settled. When you read that there are about 10 to the 80th atoms in the universe, where does that number come from? Nobody lined them up. Nobody walked the length of the cosmos with a tally counter clicking off hydrogen. And yet the figure sits in textbooks, as though someone had gone out and checked. We never counted the atoms. Not one of them. What we did instead was measure how thickly matter is spread through space, and then multiply that thinness by the size of everything we can see. That is what counting means in physics. You almost never enumerate. You find a density, you find a volume, and the number falls out of the two. So let us build the count the way it is really built, starting with the density. Empty space is not the featureless nothing it looks like from a bedroom window. Averaged across the whole universe, ordinary matter comes out to roughly 1/4 of an atom in every cubic meter. Hold the size of that claim in plain terms for a moment. Take a cube of space about waist high on every side, a little larger than a household refrigerator laid open. Somewhere in a cube that size, on cosmic average, you would find a single atom, and the rest would be vacuum. The universe, measured fairly, is emptier than almost any word we have for emptiness. Space is nowhere close to uniform. Your body holds more atoms in one fingertip than a light year of intergalactic void holds along its entire length. Galaxies are dense. The gaps between them are nearly barren, so how can one average density mean anything at all? The answer is that the lumpiness stops mattering once you zoom far enough out. Scoop up a region a few 100 million light-years across, big enough to hold thousands of galaxies and all the emptiness between them, and every such region weighs almost exactly the same as every other. At that scale, the froth smooths into a fluid, and a fluid has one well-defined density. Which leaves a harder question. How do we know that average so precisely when we cannot fly out and weigh a cube of the cosmos? The measurement comes from the oldest light there is, the faint microwave glow left over from when the universe was young and hot and filled with plasma. Before that plasma cooled, sound waves were ringing through it, and those waves behaved like a weight bouncing on a spring. The pressure of light pushed outward, the mass of ordinary atoms pulled inward with its own inertia, and the two fought to a rhythm. Add more atoms, and you load the spring more heavily, which changes how far each bounce swings and how loud it lands. That difference is frozen into the pattern of hot and cold patches we still see today, and reading the loudness of one bounce against the next tells us the density of ordinary matter to within a couple of percent. The number in the textbook is not a guess dressed up as a fact. It is an echo, measured. Now the volume. We take that density and pour it into the largest container we are allowed to use, the observable universe, a sphere reaching about 46 billion light-years in every direction from where you are lying right now. Multiply the two together. 1 atom per waist-high cube spread across a sphere that wide, and divide by the mass of a single hydrogen atom, and the arithmetic finally hands you the famous figure. 10 to the 80th. A 1 with 80 zeros trailing after it. That number is almost impossible to hold in the mind, so let me walk you toward it instead of just saying it is big. Count every grain of sand on every beach and every desert on Earth, and you land near 10 to the 19th. Nowhere close. So imagine each of those grains becomes its own entire Earth, oceans and Saharas and all, and you count the sand on all of those worlds too. Do it again. And once more, 4 times over. Only then do you approach the number of atoms sitting inside the sphere we can see. And even that staggering figure is a minority report. Ordinary atoms make up only about 5% of everything the universe contains. Most of the matter out there is dark matter, something that pulls on galaxies with unmistakable gravity yet gives off no light of any kind. We know it is there because the outer edges of spinning galaxies move far too fast to hold together on the gravity of their visible stars alone. Something unseen and heavy is gripping them, and when we add up how much, it comes to roughly 5 times the weight of every atom in the cosmos combined. Here, counting breaks in a way it did not before. We can put the dark matter on a scale because gravity reveals its total weight through the way galaxies spin and the way light bends around them. What we cannot do is count its particles because we do not know what a single one of them weighs, or whether one clean particle is even the right picture. You can weigh the invisible majority of the universe. You cannot send it through a turnstile 1 unit at a time. Then there is light itself, and the count moves again. That same ancient microwave glow is still pouring through the room you are in, unfelt and unseen. Even the emptiest patch of space, a spot with no atom in it for meters around, carries about 400 of those leftover photons in every cubic centimeter, in every volume the size of a single die on a table. Tally them across the whole observable sphere, and you reach 10 to the 90th, a full 10 billion times more photons than atoms. Riding alongside them is a second flood, the relic neutrinos, roughly 300 in every cubic centimeter, almost as thick as the light. For every particle of matter in existence, there are 10 billion particles of light with nothing to shine on, and nearly as many ghostly neutrinos slipping through all of it untouched. That 10 billion to 1 ratio is not a random accident, and it may be the most personal number in all of cosmology. In the first slice of a second after the beginning, matter and antimatter were made in almost perfect balance, and almost perfect meant almost total destruction. For roughly every 10 billion particles of antimatter, there were 10 billion and 1 particles of matter. The pairs found each other and annihilated, flashing into light, until nothing was left except that single unmatched particle out of each 10 billion. The photons still flooding your room are the ash of that vanished war. The one survivor in 10 billion is you. Every atom in your hand, every atom in every star you have ever seen, is the remainder that lived only because the early universe could not quite make its accounts balance. So which count is the count of the universe? The atoms, the dark matter we can only weigh, or the light? The question sounds like a technicality, and it is not. Before we can ask how many universes there are, we have already been forced to admit that even inside one universe, the total depends entirely on what you decide to count. Change the thing you count, and the number swings by 10 orders of magnitude without a single particle moving. There is one more thing hiding inside everything we just did, and it is the reason all of this leads somewhere rather than closing here. Every number we reached, the atoms, the photons, the neutrinos, the density, the volume, was fenced in by the same boundary. The observable universe. That sphere 46 billion light-years wide. We poured the density into that container and stopped at its walls, as if the walls were the edge of what exists. But nothing about a density says the matter halts, where our seeing halts. The container was chosen for us, by the speed of light and the age of the cosmos, not by the universe deciding to end. So what is that boundary really? And why does it sit exactly 46 billion light-years out, when the universe has only had 14 billion years to send us anything at all? Here is a contradiction you were handed a moment ago and may not have caught. The sphere we can see reaches 46 billion light-years in every direction, and the universe has existed for only about 14 billion years. Light is the fastest thing there is, and nothing has ever been given more than 14 billion years to travel. So how does the edge of the visible sit more than 3 times farther out than light could possibly have crawled in all the time that has passed? The escape from that contradiction is the single most important idea in modern cosmology. The boundary is not set by how far light has moved through a fixed and waiting space. It is set by light moving through a space that was itself growing the entire time the light was in flight. The photons reaching your eyes tonight left their sources near the beginning, and while they traveled, the distance behind them and ahead of them stretched. They always moved at the same local speed, the speed of light and no faster. The ground they were crossing simply got longer underneath them. Picture a photon crawling along a road at a fixed pace, 1 step per second, never speeding up. Now imagine that while it walks, new stretches of road are being inserted everywhere along the route, not at the finish line only, but between every pair of paving stones already laid. The photon's speed never changes, yet the total length it ends up covering is far greater than its pace multiplied by its walking time, because the road it walked grew beneath its feet as it went. That is not a trick of storytelling. It is the literal geometry of an expanding universe, and the 46 billion light-year figure is what you get when you add up all that inserted road. The way physicists add it up has a clean shape, even if the symbols look forbidding. You take the speed of light, and at every instant of cosmic history you divide it by how compressed space was at that instant. Then you sum those slivers across all of time from the beginning until now. Early on, when everything was packed close together, each second of travel bought an enormous amount of eventual distance, because that early ground has been stretching ever since. Later, the same second of travel buys less. Sum the whole history, and the total comes out around 46 billion light-years, a distance so large that if you tried to drive it at highway speed, you would need more time than the universe has existed, repeated more times than there are atoms in your body. If the far edge of the observable universe is racing away from us so fast that light struggles to bridge the gap, then those distant regions are receding faster than light itself. And relativity is supposed to forbid exactly that. Nothing outruns light. How is this allowed? The resolution is that relativity forbids one specific thing, and this is not that thing. What relativity prohibits is any object moving through space, past its neighbors, faster than a light beam next to it. A distant galaxy is not doing that. It sits quietly in its own patch of space, drifting slowly relative to everything nearby. The enormous velocity between us and it comes from all the space in between expanding at once, a swelling that belongs to the space, not a motion belonging to the galaxy. No object passes any other object. The rule stays intact, and the galaxy still recedes faster than light. If galaxies past a certain distance recede faster than light, you would expect their light could never reach us. Some of it reaches us anyway. The distance at which recession first hits light speed, called the Hubble radius, is not a fixed line. It has grown through most of cosmic history, sweeping outward over billions of years. So a photon that set out long ago from a galaxy, then receding faster than light could, as that boundary swept past it, find itself in a slower zone, and from there begin closing the gap to us. Some of the oldest light in your sky reached you only by first losing ground, drifting farther away in real distance for ages, before the moving edge of expansion overtook it and turned the journey in its favor. Standing where you are, this sphere feels like it has a rim, a place where the universe stops. It has nothing of the kind. The boundary is not a feature of space out there. It is a feature of you, of your position, and the finite time light has had to reach it. An observer sitting in one of those far galaxies, right at the edge of what we can see, is not perched at the end of anything. They sit at the center of their own sphere, 46 billion light-years in every direction from them, and a large part of what they can see is space that will remain hidden from us for as long as we exist. Think of it as countless spheres of vision, one centered on every observer everywhere, all of them the same size, all of them overlapping like soap bubbles pressed together across a surface far larger than any single bubble. Your bubble and a distant one share a lens-shaped region you can both see. Push far enough, and there are bubbles that share nothing with yours at all, observers whose entire visible universe lies wholly outside ours, with not one galaxy in common. None of these are edges. They are horizons, and a horizon is always a statement about where the watcher stands, never about where the world ends. There is a subtlety here that rewards a closer look, and it changes what the visible boundary even is. The true edge we run into is not a wall of matter, but a wall of light. Roughly 380,000 years after the beginning, the universe cooled enough for atoms to form, and in that instant, it changed from an opaque fog into something transparent. Before that moment, space was a glowing plasma, and light could not travel freely through it any more than it travels through the interior of the sun. So when we look as far as we can look, we do not reach a rim of the cosmos. We reach the last surface where that fog cleared, the oldest light able to survive the trip, still arriving now as the microwave glow from the previous chapter. Beyond it there is more universe, but it is hidden behind the brightness of its own hot youth. So the boundary that fences in every number we counted turns out to be three things at once. It is a limit set by the finite speed of light and the finite age of the cosmos. It is personal, centered on the observer, real for you and different for everyone else. And the deepest of its layers is not even the true particle horizon, but a curtain of ancient light we cannot yet see past. None of these mark a place where matter stops. Every reason we have points the other way, toward space and matter continuing well beyond the curtain, arranged by the same physics, following the same laws, on and on past anything we will ever measure. And the same expansion that carried those ancient photons to us has begun, in this era of accelerating growth, to work the other way. Driven by the dark energy pushing space apart faster and faster, The most distant galaxies are being carried beyond a second and tighter boundary, one past which no light they send from now on will ever arrive, however long we wait. The universe we can see is enormous and still coming in. The universe we could ever reach, or ever answer, is quietly narrowing. Each passing age, a few more galaxies slip across that line and go dark to us for good, not by fading but by outrunning every signal we could ever send after them. Which forces the question that the rest of this depends on. If our sphere is finite in size, and it is, then it holds a finite amount of matter, arranged in some particular way. A finite region, a finite set of ingredients. And a finite set of ingredients can only be arranged in so many distinct patterns before the arrangements are forced to start repeating. So how many distinct ways can the contents of a universe our size be put together before nature runs out of new configurations and has no choice but to build the same thing twice? The first answer that leaps to mind is infinity, and it is wrong for a reason that took some of the best minds of the last century to uncover. You might think the matter in our sphere can be arranged in endlessly many ways, because a single atom could sit here, or a hair to the left, or a hair to the left of that, with no smallest step. Position looks continuous, and continuous means infinitely divisible, and infinitely divisible means infinite possibilities. Every part of that reasoning feels solid, and the conclusion is still false. The universe does not permit infinite detail inside a finite space. To see why, you have to put two things in the same room that rarely get introduced: quantum mechanics and gravity. Quantum mechanics says information is not free. Storing a finer and finer distinction, a position pinned down more and more precisely, costs energy, and the cost climbs the more precisely you try to pin it. Gravity sets the ceiling on that bargain. Pack too much energy into too small a region in the effort to store too much detail, and the region does something drastic. It collapses into a black hole. The attempt to hold unlimited information in a finite space defeats itself, because the last increments of information bring enough concentrated energy to seal the region behind a horizon. So there is a hard limit on how much can be known about, or stored inside, any finite region. This is the Bekenstein bound, and its size depends on just two things: how big the region is and how much energy it contains. A region of a given size holds only so many bits before it cannot hold one more. The count is finite. Large beyond imagining, but finite, with a real ceiling that nature enforces by turning the overfilled space into a black hole. Now comes the part that deeply unsettled the physicists who found it. You would expect the amount of information a region can hold to grow with its volume. Twice the volume, twice the storage, the way a bigger warehouse holds more boxes. It does not work that way. The maximum information a region can hold grows with its surface area, with the size of the boundary you would draw around it, not with the space inside. A warehouse that scaled like the real universe would hold more boxes only when you enlarged its walls, and adding depth behind those walls would buy you nothing at all. The clue that forced this on us came from black holes themselves. When Jacob Bekenstein and Stephen Hawking worked out how much entropy a black hole carries, how much hidden information it swallows, the answer did not come out proportional to its volume. It came out proportional to the area of its horizon, the surface of no return. Take that surface, tile it into the smallest squares physics allows, squares 1 Planck length on each side, and the black hole's information content is 1 bit for every 4 of those tiles. the entire content of a black hole, everything that ever fell in, written across its surface at 1 bit per 4 tiny squares, with the interior adding nothing to the tally. The Planck length is the scale where space itself stops behaving smoothly, and it is small past any comparison you have ever used. It is about 100 billion times smaller than a single proton, and the proton is already 100,000 times smaller than the atom it sits inside. The surface of a black hole, or of a whole universe, is measured in tiles that small, and even so the number of them is finite, and so the information is finite. The idea stops being about black holes at this point and starts being about everything. The same reasoning applies to the horizon around us, the sphere from the last chapter. That sphere has a surface, an enormous one, and tiling it in Planck-sized squares and taking 1 bit for every 4 gives the absolute maximum information our observable universe could ever contain. The number comes out near 10 to the 122nd power in bits. Set that beside every hard drive, every book, every photograph and film and archive humanity has ever produced, which together hold something like 10 to the 24th bits. The cosmic ceiling is that entire human record multiplied by itself, and then multiplied by 10 to the 74th on top. All of recorded human knowledge is a rounding error against what a single universe our size can, at most, hold. If everything inside a region can be accounted for by bits written across its surface, then in some real sense the surface is enough. The three-dimensional interior, with all its depth and volume, carries no more information than a two-dimensional boundary drawn around it. This is the holographic principle, and it hints that the inside of a region may be, at the level of raw information, a projection of what is encoded on its edge, the way a flat sheet of holographic film stores a whole scene that springs into depth when you tilt it toward the light. The room around you feels thick with 3 dimensions, and every bit of that thickness could be spelled out on the surface of the sphere that encloses it. Now, take the final step, the one that answers the question we started with. If a universe our size holds at most 10 to the 122nd bits, then the number of distinct ways it can be arranged is 2 multiplied by itself that many times, once for each bit that could be on or off. That count comes to roughly 10, raised to the power of 10 to the 122nd. A number so large that the count of its digits alone already dwarfs everything we have ever named. To write it out in full, 1 digit per atom, you would need 10 to the 122nd atoms, and the whole observable universe supplies only 10 to the 80th. You would run out of atoms to write the number long before you finished writing down how many zeros it has. A universe is not an inexhaustible well of novelty. It is a finite object, describable, in principle, by a finite string of bits, with a definite and enormous number of distinct states it could occupy, and no more. Vast past comprehension, and still a number, still a ceiling, still something nature counts to and then stops. 10 to the power of 10 to the 122 is what the surface allows if every last tile is used to store information. The universe is nowhere near that full. When you count instead the arrangements available to ordinary matter at ordinary densities, the particles that make up stars and gas and worlds, the realistic tally is smaller, closer to 10, raised to the power of 10 to the 118. Smaller, and still a number no mind can hold, and still, decisively, finite. And the gap between the ceiling and the working total is not an idle detail. A universe filled all the way to its Bekenstein bound would be a single enormous black hole, featureless and maximally disordered, with no room in it for a star or a heartbeat or a thought. Ours sits staggeringly far below that ceiling, and only because it does can there be any structure at all, the gradients in galaxies, and the slow drift of order into disorder that we feel from the inside as the passing of time. A region the size of our horizon can be built in only finitely many distinct ways. A tremendous number of ways, but a finite one. A number you could in principle write on a list that ends. And that leaves the sharpest question yet, resting on a single further fact about the world. If the arrangements are finite, but space itself goes on without end, then somewhere out there the list must run out, and nature must begin repeating patterns it has already built. How far would you have to travel across an endless space before the arrangement of matter is forced, by sheer arithmetic, to become an exact copy of the one around you now? Start with something small enough to hold in the mind. Imagine a shelf of boxes, and inside each box a chessboard with a handful of pieces scattered on it, but only a fixed number of squares and a fixed number of pieces. There are only so many ways those pieces can sit on that board. A large number of ways, but a countable, finite one. Now, start walking down the shelf, opening box after box, each with its own arrangement. If the shelf is long enough, something is forced to happen, with no way around it. You must eventually open a box whose board is arranged exactly like one you already saw. That is the whole idea, and it has a name older than cosmology. The pigeonhole principle. If you have more pigeons than holes, at least one hole holds two pigeons, and no cleverness avoids it. Push the shelf of boxes to infinite length, and every possible arrangement does not merely repeat once. It repeats endlessly, each configuration appearing again and again, spaced out along the shelf forever. The last two chapters built exactly this shelf. A region the size of our horizon is one box. Its arrangements are finite, we counted them. And if space runs on without end, the shelf has no last box. To feel how a finite number can still outrun every intuition you own, take an ordinary deck of playing cards. Shuffle it once, and the order in your hands is almost certainly one that has never appeared before in the history of the world, because a single deck can be arranged in about 10 to the 68th ways, more orderings than there are atoms in our entire galaxy. And yet that staggering count is finite. Shuffle forever, and orders must begin to return. Enormous and finite are not opposites, and the universe runs on exactly that pairing. So the repetition is not a wild idea bolted onto physics. It is ordinary arithmetic applied to two facts we have already established, a finite number of arrangements and, if it holds, an endless space to lay them out in. Put those together and copies are not possible. They are mandatory. Somewhere out along that endless shelf, there is a region identical to the one you occupy, down to the last particle, including a copy of this planet, this room, and the person lying in it hearing these words. This is the tamest of the 4 multiverses we will meet across this journey. It invents no new laws, no new forces, no hidden dimensions, no exotic physics of any kind. It asks for one thing only, that ordinary space, running by the ordinary rules we already know, simply does not stop. We found that a region our size can be built in roughly 2, multiplied by itself 10 to the 118 times, distinct ways. The pigeonhole principle then says this: line up that many regions side by side, and you have used up every possible arrangement. The very next one has no choice but to duplicate a region you have already passed. Multiply that many regions by the width of a single region, and you get the distance to the nearest guaranteed copy, a number near 10 raised to the power of 10 to the 118 in meters. It is not merely that the figure is large, it is that the units have stopped mattering. Normally, the difference between meters and miles and light years is enormous, a light year being about 10,000 trillion meters. To convert our distance from meters into light years, you divide by that, which trims 16 zeros off the exponent. But the exponent here is a 1 followed by 118 zeros. Subtracting 16 from a number that size changes nothing a human eye could ever register. The distance to your nearest copy is the same whether you write it in inches or in the widths of the observable universe. The number has grown past the reach of measurement units themselves. A copy of the entire region around you is the strictest demand because it asks for every particle across billions of light years to match. Ask for less, ask only for a copy of you, one human body in one moment, and far less information has to line up. The nearest exact duplicate of just yourself sits much nearer, at something like 10 raised to the power of 10 to the 28 meters. Nearer, and still so far beyond our 46 billion light-year horizon that the word distance begins to feel misused. There could be countless copies of you, and every single one lies past any edge we could ever see across. These copies also arrive in a nested order that repays a closer look. The nearest ones match the least of you. Reach the closest of all and you find your body in this one instant, and nothing more promised. Travel enormously farther and you reach a copy that shares not just this moment but your whole remembered past. Every day you have lived arranged identically behind it. Farther still lies a copy of the entire Earth, every person on it doubled, and farther again a replica of the whole observable sphere, every galaxy hung in the same position as ours. Each stricter demand for sameness costs more distance, and an endless space settles every bill without strain. Every step here hangs from one word, and that word is if. If space is truly infinite, not merely vast, not merely larger than what we see, but endless in the full mathematical sense, going on with no boundary and no end. Because the pigeonhole argument needs an infinite shelf. A shelf that is only tremendously long, a universe that is huge but finite, gives you no guarantee at all. On a finite shelf, you might pass every arrangement, or you might not, and there is no theorem forcing a repeat. The copies appear only when the shelf never ends. It is not enough for space to be infinite. The matter in it has to be sprinkled with enough evenness and enough randomness that all the allowed arrangements truly get their turn somewhere. If the whole endless universe were, against all odds, a single pattern stamped over and over with no variation, you could travel forever and never find a region unlike your own, nor an exact match either. The theory that gives us reason to expect the right kind of randomness is cosmic inflation, which seeds every region with tiny independent quantum fluctuations, and that theory is the subject we are walking toward. And I want to be precise about what a copy is, because the word invites a kind of magical thinking that the physics does not support. A copy is not a twin you are connected to. Nothing passes between you. There is no thread, no sympathy, no shared feeling across the void, no way for one of you to sense or signal the other, not now, not ever. The copy is a brute consequence of counting, a region that happens by the arithmetic of finite arrangements in endless space to be built the same way yours is. And by the same, I mean matched to the finest distinction physics treats as real, every particle in the same quantum state, to the resolution we counted with earlier, not similar, not nearly alike, the same in the only sense nature keeps its books. Whether it then lives out the same life as you depends on whether the same starting arrangement always leads to the same future, a question about determinism we have not touched and will have to. Every copy, near or unthinkably far, every duplicate of this room and this breath, exists only if space itself has no end. That is not a matter of taste or interpretation. It is a property of the real universe, either true or false, and it is the kind of thing that leaves fingerprints a telescope might read. So the question stops being philosophical and becomes experimental. Have we ever looked, and has the universe ever told us, in any measurement we can trust, whether the space we live in goes on forever or quietly closes back on itself? The honest trouble is that you cannot step outside the universe to see its shape. There is no vantage point above it, no doorway you can walk through to look back and check whether space curves or runs on straight. Whatever we learn about the shape of everything, we have to learn from the inside, trapped within the very thing we are trying to measure. And yet it can be done, because shape leaves traces that an inside observer can read if the observer is patient enough and the triangle is large enough. Start on a surface, the skin of the earth. Imagine flat creatures living on it, unable to look up or down, aware only of the two dimensions they can crawl through. They could still discover that their world is round without ever leaving it. All they would need is a very large triangle. Draw a small triangle on the ground, and its three angles add up to a familiar total, the same one you learned in school. But draw a triangle spanning a quarter of the planet, one corner at the North Pole and two on the equator, and the angles swell past that total, adding up to more than they have any right to. The excess is the curvature of the sphere, revealed by geometry alone, from creatures who never once saw the sphere from outside. Our situation is the same, lifted by one dimension. We are the flat creatures, living inside three-dimensional space instead of on a two-dimensional skin, and we want to know if that space is flat or curved. A flat space obeys the geometry you were taught, triangles closing at the ordinary total, parallel lines never meeting. A positively curved space, curved like the surface of a sphere but in one more dimension, makes triangles fat, their angles summing to more, and it eventually closes back on itself, finite in size. A negatively curved space, shaped like an endless saddle, makes triangles thin, their angles summing to less, and it opens out forever. So the shape of the whole universe comes down to a single question we can, remarkably, put to a measurement. How do the angles of a cosmic triangle add up? To draw that triangle, we need a ruler of known length placed impossibly far away, and the universe left us one. Cast your mind back to the ancient microwave light, the glow from when the fog cleared. Frozen into it are hot and cold patches of a very particular size, set by how far sound could travel in the young universe before that moment, a distance we can calculate with confidence. So we know the true physical width of those patches. We know how far away they sit, at the edge of the visible. That gives us a triangle with a base of known length and a known distance, and all that remains is to measure how large the patches look in our sky. The logic then becomes clean. If space is flat, the patches should appear about 1 degree across, roughly twice the width of the full moon. If space curves positively, Like a sphere, it acts as a lens that magnifies, and the patches would look larger than 1 degree. If space curves negatively, like a saddle, the patches would look smaller, shrunk by the diverging geometry. The size we see is the answer the universe gives to whether it is finite or endless, written across the whole sky in spots of light. We measured them. The patches come in at almost exactly 1 degree, the flat space value, with no swelling and no shrinking that anyone can detect. Put in the language cosmologists use, the total density of the universe divided by the precise density that makes space flat comes out to 1, give or take about 2 parts in 1,000. Space, as far as the sharpest instruments can tell, is flat. The cosmic triangle closes at the ordinary total, and the great triangle drawn across the sky refuses to bulge or pinch. That flatness is far stranger than it first sounds, and the strangeness is itself a clue. A universe does not sit balanced on flat by accident. In the earliest moments, any faint lean toward curvature, even 1 part in 1,000,000, would have been amplified with brutal speed as space expanded, tipping the whole cosmos hard toward collapse, or hard toward runaway emptiness within its first breaths. For space to still look flat today, to 2 parts in 1,000, it had to begin flat to a precision of dozens of decimal places, poised on a knife edge with a care that borders on the absurd. Nothing in the plain story of a hot beginning explains why it started so perfectly balanced. That unexplained perfection is a loose thread, and pulling on it leads straight to the next idea. People were once taught that geometry was destiny, that a flat universe would coast to a gentle halt, while a curved and closed one would fall back and collapse. The discovery of dark energy broke that tidy rule. Our flat universe is not coasting toward rest at all. It is accelerating apart, driven by something the geometry alone never foretold. Shape and fate, once thought to be the same statement, came quietly unlinked. The first is the humble matter of measurement. 1, give or take 2 parts in 1,000, is not exactly 1. There is room in that error bar for a very gentle curvature we simply cannot yet resolve, the way a small enough patch of any curved surface looks flat to a short enough ruler. If such a curvature is hiding there, it tells us the universe curves so slowly that the whole thing, the true entirety of space, is at minimum dozens of times wider than the part we can see, and quite possibly vastly more. A firm lower bound on the size of everything, and not a proof that the size is endless. Flat does not force infinite. The two ideas feel welded together, and they come apart the moment you think about wrapping. Picture an old arcade game where a ship flying off the right edge of the screen reappears on the left and off the top returns at the bottom. The screen is perfectly flat. Every triangle on it closes at the ordinary total, and yet its surface is finite, and a straight path across it eventually returns you to where you began. Space could be built the same way, flat in its local geometry and yet folded so that traveling far enough in one direction brings you home. A flat universe can be endless, or it can be finite and wrapped, and no triangle can tell the two apart because their geometry is identical. If space folds back on itself over a distance smaller than our horizon, then some of the light coming from one direction and some coming from another would have left the same region long ago by different routes around the loop. That would print matching circles onto the ancient microwave sky, the same pattern of hot and cold appearing twice in different places. Careful searches have combed the data for those repeated circles. None have turned up. So if space is wrapped, the loop is larger than everything we can see, which hands us yet another lower bound, and still, stubbornly, not a proof of the infinite. So gather what the evidence entitles us to say. Space is flat, or so near it that any curvature lies beneath our reach. The full extent of the universe is far larger than the visible sphere, by every measurement we can make. But whether it is truly endless enough to guarantee the copies of the last chapter, remains a thing we have not shown and perhaps can never show from the inside. The tamest multiverse rests on an assumption our best data are comfortable with and cannot confirm, which leaves a strange opening. If ordinary measurement cannot deliver an infinite space, is there a theory that does not merely permit endless space but actively produces it, generating new expanse faster than anything could ever cross? And was that theory built to explain the very spots of light we just used as our ruler? It was invented to fix two embarrassments, and the universe factory fell out of it uninvited, which is part of why physicists take it seriously. The theory is cosmic inflation, and its central claim is almost rude in its simplicity. For the briefest sliver at the very beginning, space did not expand at the stately pace we see today. It doubled, and doubled again, and again, over and over, faster than anything before or since. To feel why anyone would propose something so extreme, look at the first embarrassment. The ancient microwave sky has almost exactly the same temperature in every direction, to within a few parts in 100,000. On its face, that should be impossible. Two patches of sky on opposite sides of us are so far apart that, in the ordinary history of the cosmos, light has never had time to travel from one to the other. They have never been in contact, never exchanged heat, never had any chance to settle to a common temperature. So why do they match to 5 decimal places, like 2 cups of coffee left to reach the same warmth in a room they were never both in? Inflation answers this by rewriting their history. Before the burst, those patches were not far apart at all. They sat together in a tiny region, small enough that light had crossed it easily, letting the whole patch settle to one temperature the ordinary way. Then, inflation seized that thumbnail of matched, uniform space and blew it up beyond all recognition, hurling its once neighboring parts to opposite ends of the sky. The uniformity we see is not a miracle of coordination across impossible distances. It is the fingerprint of a small, calm region stretched enormous. The second embarrassment is the knife edge from the last chapter, the flatness that had no business being so exact. Inflation disposes of it almost as a side effect. Take any surface, curved however you like, and stretch it by a stupendous factor, and any small piece of it becomes indistinguishable from flat. Blow up a wrinkled balloon to the size of the Earth, and the patch under your hand looks like a plain, level field. The universe did not begin poised on flat by some cosmic luck. Whatever curvature it had was ironed out by the sheer violence of the stretching, driven so close to flat that dozens of decimal places of precision come for free. What could physically drive an expansion like that? And here the mechanism matters. Inflation is powered by a field filling all of space, sitting temporarily in a high-energy state, a kind of loaded, unstable perch. A field in that state has a strange property that ordinary matter lacks. Its gravity pushes out instead of pulling in. Ordinary matter, by its gravity, would slow an expansion down. This field, by its negative pressure, does the opposite, feeding the expansion and driving space to grow at a runaway, compounding rate. That compounding is the whole engine, so let me make its speed concrete. The size of space during inflation grows the way money grows under relentless interest, not by adding a fixed amount each moment, but by multiplying each instant's size, setting the growth of the next. Growth like that is described by a single clean law, the size climbing as a rising exponential in time, governed by one rate. Physicists count this growth in doublings, and to erase the two embarrassments, the young universe needed something like 60 of them in a row, 60 successive multiplications, each one enlarging space by a factor of nearly 3. And the numbers that come out are savage. In far less than a trillionth of a second, a region smaller than a single proton was stretched to something you could hold in your hands, and then far beyond, multiplied in scale by a factor with dozens of zeros. Every part of the observable universe today traces back to a seed that inflation enlarged past all proportion in an eye blink shorter than any eye blink. The same process left a signature we have already been leaning on. In the quantum world, no field can hold perfectly still. The field, driving inflation, jittered with tiny quantum fluctuations, unavoidable flickers in its energy from one spot to the next. Inflation took those subatomic flickers and stretched them along with everything else, freezing them into space as faint ripples of slightly higher and slightly lower density. Those ripples are the very hot and cold patches we read in the microwave sky, and the seeds from which every galaxy later grew. The grandest structures in existence, whole webs of galaxies strung across the heavens, are quantum noise from the first fraction of a second, blown up and made permanent. Inflation has to end, or we would not be here to discuss it, and it does end, in any given place, when that loaded field finally slips off its unstable perch and rolls down to a calm, ordinary state. When it does, the enormous energy stored in the field pours out as heat and particles, and that release is what we have always called the Big Bang, the hot, dense start of a normal cosmic history. So the fiery beginning we once imagined as the start of everything becomes something smaller. It is the moment inflation stopped in our region. The words in our region are doing enormous work, and they are the hinge of the entire idea. The field does not slip off its perch everywhere at the same instant. The rolling is a quantum process, part chance, happening here a little sooner and there a little later, region by region, with no global signal to end it all at once. And while it drops out in one place, birthing a pocket of ordinary space, the regions that have not yet dropped are still inflating, still doubling, still multiplying their volume at that savage compounding rate. The fact that changes everything is a race between two runaway processes. Yes, regions are constantly falling out of inflation and settling into calm pockets. But the inflating background between those pockets is doubling so much faster than they can drain away that the total inflating volume does not shrink. It grows without limit, forever. For every pocket that stops inflating and cools into a universe like ours, the surrounding sea has already spawned far more than enough new inflating space to replace it, and then some. The draining never catches up. The sea only ever gets larger. This is why it earns the name eternal inflation. Not because any single place inflates forever, but because the process as a whole, once lit, can never be put out. Somewhere it is always still going, always spinning off fresh pockets, each one a hot new beginning, a big bang that to its inhabitants looks like the birth of all there is. Our entire universe, everything from the last 5 chapters, is one such pocket, one bubble that stopped inflating and cooled 14 billion years ago. Beyond its walls, the machine is still running, and it has never, for one instant, stopped making more. I should be plain about how much of this rests on solid ground and how much is reaching past it. The core of inflation stands on real evidence. It called for a flat universe before we measured one. It forecast the particular size and spread of the microwave spots, and it even predicted a faint tilt in that pattern that later observations went on to confirm. But the step from inflation happening to inflation being eternal is an extrapolation, riding on how the field behaves in conditions we cannot yet test. Some versions of the theory are eternal and some are not, and a number of careful physicists doubt the eternal picture altogether. The machine is a serious possibility, not a settled fact, and the fair word for it is still maybe. If the machine has been producing pockets without pause and will go on producing them without end, then the tally of universes it makes is no longer a matter of arrangement or geometry. It is a matter of how fast a factory runs against how long it runs, and the second number has no ceiling. So what happens to the count when you try to add up universes from a machine that never switches off and produces new ones faster than anything could ever tour them? Try to run the tally, and the first thing you meet is a race. The same race that made inflation eternal, now viewed as an accountant would view it. On one side, the inflating sea multiplies its volume. On the other, bubbles keep nucleating inside it and draining volume away into calm, finished pockets. The whole question of the count comes down to which side wins and by how much. Look first at the growth, because its speed is easy to understate. The inflating volume does not just expand, it expands in all three dimensions at once, each of them stretching exponentially, so the volume climbs as the cube of that already ferocious growth. Put in plain terms, every time the driving field ticks forward by one step of its natural clock, the inflating volume multiplies roughly 20-fold. One tick, 20-fold. Another tick, 20 times that again. A dozen ticks in, and the volume has grown by a factor larger than the number of atoms in a galaxy, and the field's clock ticks in slivers of time far shorter than anything you could name. Now the draining. Bubbles form by a quantum process, a kind of tunneling in which a patch of the field spontaneously slips through to the calm state, the way a ball trapped in a valley can, by the rules of the quantum world, appear on the far side of a hill. It never had the energy to climb. That tunneling is rare. It is exponentially suppressed, meaning it happens so seldom per unit of volume that in any small region you would wait an eternity to see one. So the drain is slow, and here the two rates meet the only fact that matters for the count. As long as the volume multiplies faster than the bubbles can drain it, the inflating sea does not merely survive. It grows without end, and the pockets forming inside it, however many, never make a dent. There is more to picture in a single bubble than a patch quietly going calm. Once a bubble nucleates, its wall races outward at very nearly the speed of light, eating into the surrounding false vacuum and converting it to the true, calm state, so the pocket swells at a furious pace of its own. You might think two such bubbles would soon meet and merge into one. They almost never do. The inflating space between any two bubbles is stretching faster than their walls can close the gap, so the pockets are carried apart even as they grow, sealed off from one another for good by an ever-widening sea neither can cross. Each pocket lives out its history alone, walled away from every other by the same expansion that made them. There is a clean way to state the tipping point. If the fraction of volume that decays into bubbles during one tick of the field's clock is smaller than the roughly 20-fold amount the volume grows in that same tick, then inflation is eternal and the number of bubbles has no ceiling. The real universe sits deep on the eternal side of that line, not barely across it, but far across, because the tunneling is so heavily suppressed. Imagine trying to empty a pool through a straw while a fire hose fills it. No number of straws, no matter how many bubbles drain away, can lower the water when the hose outpaces them all by factors of billions. The pool only ever rises. The exact figures here, the 20-fold growth, the depth of the suppression, depend on the detailed shape of the field's perch, which we do not yet know. They are illustrative of a broad family of models rather than measured quantities. What survives across almost all of that family is the conclusion itself, that once inflation of this kind begins, the eternal outcome is difficult to avoid. So the count of pockets grows the same way the volume does, exponentially and without limit. Wait longer, and there are more bubbles. Wait longer still, and there are unspeakably more. The number climbs past every finite figure we have used in this whole account, past the atoms, past the arrangements, past the distance to your nearest copy, and it does not slow, and it does not stop, because the machine driving it does not stop. Whatever number you propose as the total, wait one more tick of that clock, and the true number has already blown past it many times over. The subtlety that keeps this honest is also the seed of the real trouble ahead. At any given moment, the number of pockets is finite. Enormous, growing, but finite. A definite count you could in principle write down if you froze the machine at any chosen instant. The infinity only lives in the limit, in the fact that there is no last tick, no final moment when the counting is done. This is the old difference between two kinds of infinity, and it matters more here than almost anywhere. There is the infinity you can complete, a set that simply exists, all its members present at once. And there is the infinity you can only approach, a process that never finishes, always offering one more than whatever you have counted, never handing you the whole. Eternal inflation gives the second kind. Always more pockets, never all the pockets. That second kind of infinity carries a quiet poison. When there is never a final count, the answer to how many depends on where you choose to stop, and different stopping points give wildly different answers. Freeze the machine early, and the youngest pockets, the ones just formed, overwhelm the tally because the factory has been doubling its output the entire time, and the most recent batch always dwarfs everything that came before. Freeze it later, and the balance shifts yet again. There is no moment that is the right moment, no natural place to draw the line, and the fraction of pockets that look like ours slides around depending entirely on a choice we have no principled way to make. And now the fact that turns this from a large number problem into something stranger, the fact that will break the counting entirely in a moment. Each bubble, seen from outside in the inflating sea, is a finite thing, a droplet nucleating in a vast ocean. But step inside one, into a pocket like our own, and the geometry plays a trick that general relativity forces on us. From within, the bubble does not look finite at all. The way its interior slices up space and time, an inhabitant of the bubble sees an open, negatively curved universe that stretches on without bound, spatially infinite from the inside though finite from without. So we do not merely have an endless procession of pockets. We have an unbounded, ever-growing number of bubbles, and each single one of them is, to those living in it, an infinite universe in its own right. And these pockets need not resemble one another. When the field rolls off its perch, it does not have to settle into the same calm valley every time. Different pockets can come to rest in different states, and the state a pocket freezes into fixes the physics that will hold there ever after. The masses of its particles, the strengths of its forces, the very ingredients available to build anything at all. So the endless list is not endless copies of one universe. It is an endless variety, pocket after pocket with its own rules, and we will return to just how much variety in a later chapter. Take in the shape of that for a moment, because the counting has quietly changed character. We began this chapter trying to add up universes the way you would add up coins, expecting a number, however vast. What we have instead is infinity, layered inside infinity, an endless list of pockets with no final entry, and every entry on the list an infinite world of its own. The tools that served us through the finite chapters, multiply the density by the volume, line up the arrangements, measure the triangle, have nothing left to grip. You cannot multiply your way through this. There is no largest term to anchor on, no total to divide into. If the multiverse offers an endless supply of pockets, and within them an endless supply of everything, then any question that begins with how many, or how likely, or how common, is now a question about comparing infinities. And comparing infinities is not the safe arithmetic it pretends to be. So when a physicist asks something as innocent as whether a universe like ours is typical or rare among all the pockets, what exactly are they dividing by when the thing on the bottom of the fraction has no end? The trouble hiding in that fraction is older than cosmology, and you can see it whole in the plainest numbers there are, the counting numbers 1, 2, 3, and on. Ask a question that sounds like it has an answer. What fraction of them are even? Your instinct says half, and your instinct can be talked out of it in under a minute. One honest way to count runs like this. Line up the whole numbers against the even numbers and pair them off, 1 with 2, 2 with 4, 3 with 6, 4 with 8, each whole number matched to its double, forever. Not a single number on either side is ever left without a partner. By that reckoning, there are exactly as many even numbers as there are numbers altogether, and the fraction that are even looks like the whole of them, like 1. Now count a second honest way. Walk up the number line and tally as you go, and at every stage about half the numbers you have passed are even, 1 even for every odd, all the way up. By that reckoning, the fraction that are even is 1/2. Same numbers, same question, 2 flawless methods, 2 different answers. It gets worse, and the worst part is the lesson. You are not stuck between 1 and 1/2. By choosing how to order the numbers as you count them, you can make the fraction of evens come out to anything you please. List 2 evens, then 1 odd, then 2 evens, then 1 odd, and the evens seem to make up 2/3. Reverse the recipe and they make up 1/3. The fraction is not a fact about the numbers at all. It is a fact about the order you chose to walk through them, smuggled in and dressed up as a discovery about the numbers themselves. That is the whole disease, and now watch it infect the multiverse. When a physicist asks what fraction of pockets are like ours, or how likely a universe is to have our physics, they are asking exactly the even number question, only with universes in place of integers. The pockets are endless. The ones like ours are endless. And the fraction, the thing they want to call a probability, depends entirely on the order in which you agree to count the pockets, an order that nothing in the physics hands you for free. To get any number out at all, you have to choose a rule for how to march through an infinite multiverse, and that rule has a name. Cosmologists call it a measure. A measure is usually built as a cutoff, and the idea is reasonable on its face. You cannot count an infinite collection, so you stop early. Count only the pockets that formed before some chosen moment, or only those within some chosen enormous volume. Work out the fraction among that finite haul, and then let the cutoff slide outward toward infinity, and see what the fraction settles to. It is a sensible plan, and it runs straight into the even number trap. Cut off the infinite multiverse one way, by counting up to a certain time, and you get one set of probabilities. Cut it off another way, by counting out to a certain size, and you get a different set. Both are defensible. Neither is forced. And they disagree, sometimes about whether a universe like ours is overwhelmingly common or vanishingly rare. To feel how badly this can break, look at the measure that seems most natural of all, the one that simply counts by the ticking of time. Recall from the last chapter that the machine doubles its output relentlessly, so the youngest pockets always outnumber the older ones by staggering factors. Count by time, and that lopsidedness dominates everything. The overwhelming majority of pockets at any cutoff are freshly formed, so the typical observer this measure predicts should find itself in a universe far younger than ours, under a sky still hot and dense, not in a cool, quiet cosmos 14 billion years old. By that measure, our own existence, calm and late and unremarkable, is wildly improbable, almost impossible. This is the youngness paradox, and it is not a small technical wrinkle. It is a supposedly natural rule for counting universes, predicting, with confidence, that we should not be here to notice it. There is a second symptom just as unsettling. Under some measures, the most common conscious observers are not creatures like us at all, evolved slowly on planets, but fleeting flickers, brains that assemble themselves for an instant out of random thermal noise in the far future of an old, cold universe, complete with false memories of a life never lived. If a measure predicts that most observers are such flukes, then you, statistically, are probably one of them, and your memory of the last minute is a fabrication. A theory that predicts that undermines its own evidence, since it gives you no reason to trust a single thing you observe. Cosmologists use this as a filter, throwing out any measure that drowns the multiverse in these thermal ghosts. But throwing out measures by hand, because we dislike what they predict, is not the same as deriving the right one. And this is the pattern that exhausts the whole enterprise. Adopt the measure that counts by time, and the youngness paradox says we should not exist. Switch to a measure that counts by the growth of scale instead, and the youngness trouble eases, but the thermal ghosts come flooding back in, or some new absurdity appears in their place. Every rule that quiets one pathology seems to wake another somewhere else. After decades of this, no proposed measure has emerged clean, agreeing with what we see without needing to be hand-tuned to do so. So the honest state of the field, named plainly, is this. The measure problem is unsolved. There is no agreed-upon rule for counting an infinite multiverse, no principle that singles one out as correct, and the candidates on offer give clashing answers to the questions we most want to ask. And the sharpest voices raising it are not outside critics, but the very people who built the theory: Alan Guth, Andre Linde, Alexander Vilenkin, the founders of inflation themselves, who have spent decades circling the problem without settling it. They do not have a consensus, only a collection of proposals, each with its virtues and each with its own pathologies. Until that changes, Eternal inflation cannot deliver a clean probability for anything, cannot tell us whether our universe is typical or freakish, cannot even give a defensible meaning to the phrase "how many." The counting has not just grown hard. It has lost its footing entirely. The root of it is deeper than any single bad rule. Probability only means something when there is a well-defined pool to draw from and a settled way of weighing its members. An endless multiverse with no forced measure has neither, and so the ordinary machinery of probability has nothing solid to stand on. This is not a small matter, because the one tool physicists hoped would rescue prediction from all this endlessness is the idea of the typical observer, the assumption that we should expect to find ourselves among the more common kinds of inhabitants. That assumption needs a measure to define what common even means, and the measure is exactly the thing we do not have. The rescue depends on the very piece that is missing. Some physicists draw a hard conclusion from this. If a theory cannot, even in principle, say what it expects us to see, then it has drifted outside the ordinary practice of science, which lives and dies by holding predictions against measurements. Others hold that the measure problem is a stubborn technical knot rather than a fatal flaw, and that a principled rule will be found in time, the way earlier puzzles yielded to patience. Both camps are staring at the same fact. The multiverse of eternal inflation, as it stands today, does not tell us how likely we are, and no one has yet made it. Up to here, and the numbers, however vast, were still numbers. Now the very question of how many has dissolved in our hands, not because the answer is too big to write, but because the question stopped being well posed the moment the multiverse became truly infinite. So we are forced to change what we are counting. If we cannot count how many universes there are, perhaps we can count something firmer, something finite hiding inside all this endlessness. Not how many pockets exist, but how many truly different kinds of pocket are even possible. How many distinct sets of physical laws sit on the menu that the machine is drawing from? The most developed answer we have to that new question comes from string theory, and it arrives with a number attached that has become almost famous, 10 to the 500. Before the number can mean anything, you need the one idea that generates it, and it is an idea about dimensions. String theory only holds together mathematically if space has more dimensions than the 3 we move through. Not 3, but 9, with the extra 6 folded away so tightly that we never stumble into them, curled smaller than any distance we can probe. The move that matters is what those hidden dimensions do to the physics we can see. They are not idle. The precise shape into which those 6 extra dimensions are folded decides the rules of the visible world, which particles can exist, how heavy they are, how strongly the forces pull, even the value of that stubborn cosmic energy we met earlier. Change the folding, and you change the laws. Think of a wind instrument, where the length and shape of the hidden air column inside decides which notes can sound. 2 horns look similar from outside, yet one plays a scale the other cannot reach, and the difference lives entirely in the shape of the cavity within. The folded dimensions are that cavity, and the physics we observe is the note that comes out. The reason the shape reaches so far into the physics is what the theory says matter is made of. At the smallest scale, particles are not tiny points, but tiny vibrating strings, and a string, like a plucked wire, can vibrate in many distinct patterns. Each pattern of vibration shows up to us as a different particle. One note heard as an electron, another as a quark, another as a carrier of force. Which patterns are allowed, and what energies they carry, depends on the geometry of the folded space the string is threading through. So the shape of the hidden dimensions does not merely tint the physics. It writes the entire catalog of what can exist. So the number of possible universes, of possible sets of laws, becomes the number of distinct ways those 6 dimensions can be folded. And that number is where the counting finally has something finite to bite on. The folded shapes are riddled with holes, in the way a pretzel or a slab of Swiss cheese is riddled with holes, except that a typical one of these shapes has not 1 or 2 holes but several hundred independent ones. Through each hole you can thread a kind of field, a flux, and the crucial fact is that this flux does not come in any amount you like. It is quantized. It comes only in whole units, the way a rubber band can be wound around a post 0 times, or once, or twice, but never 1.5 times. Through each hole, some whole number of flux units, and no fraction between. Now the arithmetic writes itself. Suppose there are 500 holes, and through each you may thread anywhere from none up to 9 units of flux, 10 choices at every hole. The holes are independent, so the total number of distinct threadings is 10, multiplied by itself 500 times, once for each hole. 10 to the 500. Every one of those threadings folds the hidden dimensions a little differently, and so every one of them is a different set of physical laws, a different universe recipe waiting to be built. The menu the last chapter asked for turns out to have something like 10 to the 500 dishes on it. That number is best felt against the ones we already have. The atoms in the entire observable universe came to 10 to the 80th. 10 to the 500 is not a little larger than that. It dwarfs it past any intuition. Take those 10 to the 80th atoms, and imagine each single atom swells into its own whole observable universe, packed with its own 10 to the 80th atoms. Then do it again, each of those atoms becoming a universe, and again, 5 or 6 rounds of that dizzying nesting. Only somewhere out there do you finally reach the number of recipes string theory lays on the table. A menu longer than the universe has particles to write it with. Here the 2 halves of this journey lock together, and it is the reason the landscape matters rather than being idle mathematics. That menu of 10 to the 500 recipes would be a curiosity if nothing ever cooked from it. But recall the machine from a few chapters back, the eternal inflation that never stops making pockets. That machine does not just make pockets, it tunnels between these recipes, each new bubble settling into one folding or another as the field drops into a different valley. So the endless factory and the finite menu are made for each other. The factory supplies the infinite number of universes, and the menu supplies the finite number of kinds they can be. There may be infinitely many universes, an unbounded, uncountable flood of pockets. Yet the number of truly different kinds among them could still be finite, capped at something like 10 to the 500. An endless library with a finite number of distinct books, every title printed in infinitely many copies. This is the firmer thing we went looking for when the raw count collapsed, a finite figure standing inside the infinite. Not how many universes, but how many possible ways to be one. Every recipe on the landscape comes with its own value of the cosmic energy filling empty space, the quantity driving the accelerating expansion we met earlier. Across 10 to the 500 recipes, that energy takes 10 to the 500 different values, sprinkled all the way from enormous down to almost nothing. With a menu that vast, a tiny handful of recipes by sheer weight of numbers, will happen to land on the absurdly small value we measure in our own sky. Hold that thought. It is about to become the closest thing this entire subject has to a testable prediction. String theory, for all its mathematical depth, has never been confirmed by a single experiment, not one. The 10 to the 500 is an estimate, resting on assumptions about how many holes these shapes have and how much flux each can hold. And the true figure could be very different, larger or smaller, or the counting could be flawed in ways we have not seen. The very word landscape for this menu is only about 2 decades old, given its name by the physicist Leonard Susskind, and the picture has been argued over from the day it appeared. It is a young idea, still shifting under debate, not a finished map of anything. Not every recipe that looks consistent up close can be completed into a full, working theory of quantum gravity. Many that seem to belong on the menu turn out, on closer inspection, to be forbidden, exiled to what physicists wryly call the swampland, as opposed to the true landscape of workable recipes. How large the real landscape is after the swampland is drained, and whether a recipe matching our own universe is even guaranteed to survive on it, are open and hotly argued questions. The deepest dispute of all is whether a theory this permissive predicts anything at all. One camp sees a fatal weakness. A framework that allows 10 to the 500 outcomes, they argue, can be twisted to fit whatever we observe after the fact, and a theory that can accommodate anything forecasts nothing. The other camp sees the opposite, a feature rather than a bug, because a vast menu of constants is precisely what you would need to explain why ours are so strangely, delicately suited to our being here, once you ask which recipes could ever produce an observer to read them. That second thought is not idle speculation. It led, decades ago, to one of the only successful predictions this entire field of ideas has ever made, a prediction about the very cosmic energy we keep brushing against. Someone used a menu much like this one to guess the value of a number before anyone had measured it, and when the measurement came, it was close. So how do you predict the properties of the universe you live in? By reasoning about all the universes you do not. The number that most needed explaining was the one we have kept brushing past, the energy of empty space itself. Quantum theory is emphatic that a vacuum is not empty. Even with every particle removed, space seethes with fields flickering in and out of existence, and all that flickering should carry energy, a weight belonging to nothingness itself. When physicists estimate how much, the answer is catastrophic. The vacuum should be so dense with energy that it would tear every structure apart, and the amount they predict overshoots what we observe by a factor of 10 to the 120. The estimate is not some exotic guess. It comes from adding up the restless energy of every quantum field, one vibration mode at a time, across all the scales our physics reaches, and the sum it returns is monstrous. Register that for what it is, the most spectacular failure of prediction in the history of science. A 1 followed by 120 zeros, the gap between what our best theory of particles says the vacuum should weigh and what the universe shows. No mistake, anywhere else in physics comes within 100 orders of magnitude of being this wrong. And the puzzle has a cruel second edge. The true value is not 0, which might have hinted at some clean symmetry forcing it to vanish. It is tiny, but real, a faint positive energy that we now know is present, driving the gentle acceleration of the cosmos. Small enough to demand an explanation for its smallness, and not so small as to be nothing, which is somehow the hardest case of all. For decades, this sat as a pure embarrassment, 120 decimal places of fine-tuning that nobody could motivate. To land on the value we see, the giant contribution from the quantum fields and whatever pushes against it must cancel with a precision of 120 digits, agreeing place after place after place, and then, in the 121st, failing to cancel by the faintest sliver, leaving exactly the whisper of energy that now fills our sky. A cancellation tuned that finely all but screams for a reason. Then, in 1987, Steven Weinberg tried a move that most physicists found distasteful, and that turned out to work. He did not try to derive the value from a deeper law. He asked a different question entirely. If this energy takes many different values across many different universes, which values could possibly host someone to measure it? The landscape from the last chapter is exactly what makes that question legitimate. A menu on which the vacuum energy is scattered across a huge range, universe by universe. Weinberg did not need string theory to say it. He needed only the supposition that the value varies and that we, being here, are not free to find ourselves just anywhere. The distaste was understandable. Physics had always aimed to pull its numbers out of deeper laws, and this felt like surrender, or worse, like smuggling purpose into the equations. But the logic is humbler than it first appears. The same plain logic that explains why we find ourselves on a planet at a comfortable distance from its star. Not because anything arranged that distance for our benefit, but because we could only ever have arisen somewhere the distance was already right. This kind of reasoning had been floated by Brandon Carter and others in the 1970s under the name the anthropic principle, and Weinberg simply put it to work on the vacuum energy, with nothing more mystical than that involved. A positive vacuum energy pushes space apart, and the larger it is, the harder and sooner it pushes. Now set that against what has to happen for observers to exist. Matter must first gather, under its own gravity, into dense clumps, the seeds of galaxies, the cradles of stars and planets. That gathering takes time, hundreds of millions of years of patient falling together. But a large vacuum energy does not grant that time. If it is too strong, it flings space apart so quickly that matter is pulled away from itself before it can ever clump, and the universe races into cold emptiness with no galaxy ever forming, no star, no chemistry, no one. So the window is set by a race against a deadline. Gravity is trying to build galaxies. Vacuum energy is trying to end the building. If the vacuum energy is small enough, gravity wins the early rounds, galaxies form, and only then does the acceleration take over, too late to stop what has already been made. If it is too large, the acceleration wins first, and the universe is sterile. Observers can only arise in pockets where the vacuum energy falls below that threshold, a narrow band near the bottom of the enormous range the landscape allows. Weinberg did not simply say the value should be small. He reasoned that among all the pockets able to form galaxies, most of the galaxies, and so most of the observers, would sit in universes where the vacuum energy is as large as it can be, while still permitting structure, pressed right up against the top of the habitable window rather than far below it. Which meant a specific expectation. We should measure a vacuum energy that is not zero, but a modest few times the density of matter itself, right at the edge of what life allows. He wrote this down at a time when nearly every physicist assumed the vacuum energy was simply zero, waiting for some undiscovered principle to explain the emptiness. 11 years later, the universe answered. In 1998, Two teams tracking exploding stars in distant galaxies, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, found that the expansion of the cosmos is not slowing down as everyone expected, but speeding up. The acceleration meant a non-zero vacuum energy, present and pushing, making up most of the universe, about 70% of everything, with all matter accounting for only 30%. That put the vacuum energy at a couple of times the density of matter, squarely inside the band Weinberg had marked out. And its value came in where Weinberg had pointed, a small positive number, a few times the density of matter, within roughly a factor of 10 of his anthropic estimate. A guess made by reasoning about universes we cannot see had landed near a number nobody had yet measured. The hit was to within an order of magnitude, not a precise bullseye, and the measured value sits a little below Weinberg's central expectation, close enough to impress and loose enough to argue over. The prediction also leaned on choices, on assuming the vacuum energy is equally likely across its range, and on counting observers by counting galaxies. Change those assumptions and the predicted value shifts. And underneath it lurks the very trouble from 2 chapters ago. Because to say most observers see a certain value, you need a way to weigh observers across the multiverse, and that is the unsolved measure problem, wearing a different coat. And large surveys of the sky are still testing whether this energy holds perfectly steady or drifts ever so slightly over cosmic time, a question whose answer could reshape the entire argument yet. So what does the whole episode establish? Laid out plainly? Not proof. A theory being consistent with one measurement, even a striking one, is a long way from being confirmed, and there are rival ideas that might yet explain the small vacuum energy with no multiverse at all. But it remains the single moment when this entire tower of reasoning, the pockets, the landscape, the anthropic filter, reached out and touched a real number in the sky and came close. It is more than a curiosity and less than a proof. It is the strongest card the multiverse holds, and it is a single card. Every universe we have counted so far shares one feature. It lies somewhere out there, beyond our horizon, past the walls of our pocket, out along the endless shelf, always in some other place we can never reach. But there is a wholly different proposal, born not from cosmology, but from the physics of the very small, in which the other universes are not far away at all. They are not out there. They are right here, layered over this exact room, splitting off from it every time a single particle is forced to choose. To understand the strangest multiverse of all, you have to start with the thing quantum mechanics is built around, an object called the wave function. It is the most successful description of reality we have ever written, and it says something unsettling about a particle before you look at it. An electron does not sit at one place with one definite spin. It exists as a blend of every possibility at once, here and there, spinning one way and the other, all of it held together in a single mathematical object that carries the whole spread of what could be. You can watch that blend reveal itself in the plainest experiment there is. Send single particles, one at a time, at a barrier with 2 narrow slits, and let them land on a screen behind it. Each particle strikes as a single dot, so you might expect 2 simple stripes to build up behind the 2 slits. Instead, a pattern of many bright and dark bands slowly appears, the signature of waves overlapping, some reinforcing and some canceling. Each lone particle went through both slits at once as a blend and interfered with itself on the way. That interference is the superposition made visible, real possibilities overlapping, and it is exactly the delicate overlap that the rest of this chapter is about to describe losing. That object evolves by one clean rule, and the rule is as smooth and reliable as anything in physics. It is the Schrödinger equation, and it tells the wave function how to change from one moment to the next, gently, continuously, with no jumps and no surprises. If you know the wave function now, the equation tells you exactly what it will be later, every possibility flowing forward together in lockstep. Nothing about that evolution ever picks a winner. The blend of possibilities just keeps flowing, deterministic and complete. And that is where the trouble has lived for a century. Because when you finally measure the electron, you never find the blend. You find one thing, here or there, up or down. One definite outcome every time, and the rest of the spread is simply gone. The smooth equation says the possibilities all flow forward together, yet the moment of looking delivers a single answer, as if the whole rich superposition collapsed to a point the instant you paid attention. The standard response, the one taught for generations, was to write that collapse into the theory by hand. Alongside the smooth equation, you add a second rule. When a measurement happens, the wave function abruptly jumps, at random, to just one of its possibilities, with the odds set by how much of the blend that possibility held. Two rules, then, stitched together. A smooth flow when no one is looking, and a sudden random collapse when someone is. It works, in the sense that it predicts what we see. But look closely, and it is a strange, ugly seam. What counts as a measurement? Why does looking trigger a different physics than not looking? What size must a thing be, what kind of thing, to make the collapse fire? The theory that describes reality more precisely than any other never says. It just tells you to switch rules at a moment it cannot define. In 1957, a graduate student named Hugh Everett looked at that seam and made a proposal of startling nerve. What if there is no second rule? What if the collapse never happens, and never needs to? What if the only thing that ever occurs, at every scale, in every situation, is the smooth flow of the Schrödinger equation, and nothing else at all? Delete the collapse. Keep the one rule we can write down, and follow it without exception, wherever it leads. Follow it, and watch where it leads. When your measuring device interacts with the electron in its blend of up and down, the device does not force a choice. It joins the blend. The wave function grows to include a version where the electron is up and the device reads up, added to a version where the electron is down and the device reads down, both together, still flowing forward as one. And when you read the device, you join too. The blend climbs into you, a version of you that saw up alongside a version that saw down, each of them certain, each seeing a single definite result, neither aware of the other. The superposition did not vanish when you looked. It swallowed you. These are the branches, and this is the heart of the many worlds idea. Every version is equally real, equally physical, equally you. There is no fact about which outcome truly happened, because they all happened, each in its own strand of the one great wave function, running on side by side. The single rule we trust, taken at its word and never suspended, does not give one world with random jumps. It gives many worlds with no jumps at all. Notice what this does to chance itself. The evolution is perfectly deterministic, with no randomness anywhere in the equation, every branch fixed in advance by the smooth flow. The only thing that feels like luck is which branch you happen to find yourself in afterward. The roll of the dice is replaced by the certainty that every face comes up, each in its own world, and the sense of a random result is just your view from inside one strand of a wholly determined whole. The natural protest is the right one to raise. If I am constantly splitting into blended versions, why does my experience feel so seamless, so singular? Why do I never sense the other branches or watch them blur into mine? The answer is a real physical process, and it has a name: decoherence. A lone electron can hold its blend delicately, its possibilities still able to overlap and interfere. But the instant that blend spreads into something large, a device, the air, the light in the room, your own brain with its uncountable particles, it becomes hopelessly entangled with all of them. And once the possibilities are tangled through trillions upon trillions of particles, they lose every practical ability to reach back and interfere with one another. They still exist, side by side, but sealed apart, each branch now blind and deaf to the rest. Decoherence happens with almost unimaginable speed. For anything larger than a stray particle, the branches separate in a sliver of time so short it makes a billionth of a second feel like a long afternoon. That is why the world looks solid and single. The splitting is not gentle or gradual to your senses. By the time any thought forms about what you saw, the branches have already parted, cleanly and permanently, faster than experience can register. Now the correction that keeps this from becoming a cartoon, because the picture invites a wrong one. Nothing flies off into space when a branch forms. No new universe is manufactured, no fresh region of matter conjured, no explosion of duplicate rooms hurled apart. There is one wave function in one space, and branching is nothing more than that single object developing parts that no longer speak to each other. The other branches are not far away. There is no distance to them at all, no direction you could point. They are laid directly over this room, sharing its every point, differing only in that they and you can no longer touch. It would be fair to expect an idea this wild to sit at the fringe, and it does not. Many working physicists take it seriously for a simple reason. It is the most economical reading of the theory, the one that removes a rule rather than adding one, quantum mechanics taken literally and asked to explain itself with nothing extra. But it carries a real cost that honest supporters admit. If every outcome happens, then what can it even mean to say one outcome was more probable than another? And where do the familiar odds of the quantum world come from when nothing is ever left out? That question does not have a settled answer, and we will meet it again before this branch of the story closes. So this multiverse is unlike every one before it. It asks for no endless space, no extra dimensions, no bubbles beyond the horizon. It asks only that we take the one equation quantum mechanics has always used and stop making an exception every time we look. The other worlds, if this is right, are not out past the edge of anything. They are here, stacked in the same instant, as close as your own nebula-mixed heartbeat. Which turns the question of this whole journey inward and makes it suddenly, alarmingly concrete. If reality branches at every quantum event, and quantum events are happening in their multitudes inside you right now, then how many branches have peeled away in a single quiet breath? Every quantum event with two distinguishable outcomes, once it decoheres, turns one branch into two. Two outcomes become two branches, and if a second event follows, Each of those splits again, giving 4, and a third gives 8, and the count climbs the way a single grain on a chessboard becomes 2, then 4, then a heap that buries the board. After a run of such events, the number of branches is 2 multiplied by itself once for every event that has happened. So, the whole question turns on how often those events happen, and the answer is difficult to feel, because the rate is monstrous. Decoherence is not rare, saved for laboratories and careful measurements. It is the most common thing in the world. Every time a molecule of air collides with another, every time a photon scatters off a surface and carries away the faintest record of where something was, a distinguishable outcome has been registered by the environment and a branching has occurred. In a single cubic meter of the air around you, molecules are colliding on the order of 100 trillion times every second. Each collision a candidate for splitting the wave function further. The branchings are not a trickle. They are a roar, everywhere, constant, in every scrap of matter warm enough to move. And notice what does the branching, because a myth has grown up around this. It is not a conscious mind that splits the world, not the act of a person noticing. The branching is done by the environment itself, by any stray particle that ends up carrying a record of what happened, whether or not a single living thing is present to know. A photon bouncing off a dust mote in an empty room, taking away the news of where the mote was, has already branched the wave function there in the dark. Consciousness has nothing to do with it. The universe measures itself ceaselessly, with every collision, and no observer is required for any of it. Feed a rate like that into a doubling, and the arithmetic goes somewhere violent. 2 multiplied by itself 100 trillion times, and that only for 1 cubic meter, and only for 1 second. The number of branches after even a moment of ordinary life is so large that the exponent alone, the count of how many times 2 has been multiplied, already runs past the number of particles in the galaxy. Keep the clock running, and it climbs without any visible ceiling, a tower of doublings stacked on doublings, apparently outrunning every number this entire account has built. The atoms, the arrangements, the pockets, all of it left behind. But something has to be wrong with that picture, and finding the flaw is where this chapter earns its place. Cast your mind back to the chapter on how many ways a universe can exist. We found a hard ceiling there, set by the physics of information itself. The observable universe can be in, at most, about 10, raised to the power of 10 to the 122 distinguishable states. That was not a number about storage or about branches. It was the total count of truly different configurations this much space and energy can hold. Full stop. Now put the 2 ideas in the same room, because they cannot both run free. A branch is not some ghostly extra thing floating beside reality. A branch is a distinguishable state of the one-wave function, a version of the world that differs in some detectable way from the others. And the number of distinguishable states the universe can hold is exactly the ceiling we just recalled. So the count of branches cannot climb past it. 2 strands that differ only by the position of a single particle shifted less than the smallest meaningful distance are not 2 branches at all, but 1, since nothing in the universe could ever tell them apart. Only truly distinct configurations count, and their number is fixed and finite. The runaway doubling does not go on forever. It runs headlong into the same wall that limits how many ways a single universe can be arranged at all. And that collision tells us something we might have missed. The branches are not new universes being added to reality. one fresh cosmos manufactured with every collision of air. If they were, they would need somewhere to be stored, some new information capacity conjured out of nothing each time, and there is none to be had. What is happening is stranger and quieter. The fixed, finite space of possible configurations, the same one we counted long ago, is being carved into ever finer pieces. Branching does not add to the total of what can exist. It divides what already can exist into distinguishable strands. The entire many worlds multiverse, every branch that has ever formed and every branch that ever will, fits inside the information capacity of a single universe. It needs no more room than one cosmos, because in a real sense, it is one cosmos, read all the way down to its finest grain. The branches are not a larger reality stacked somewhere outside ours. They are the complete, exhaustive description of this one, every possibility it holds spelled out at once. The popular image has the universe forever spawning new worlds, the pile of realities growing without limit, each choice minting fresh copies of everything. That is not what the mathematics allows. There was always a finite set of ways the world could be, decided by the information a universe our size can hold. Decoherence does not enlarge that set. It sorts reality into the members of a set that was always finite, always capped, always the same size it was before you started listening. The worlds are not accumulating. They were, in a sense, always there as possibilities, and branching is only the act of separating them out. In delicate laboratory experiments, if the record that distinguished two possibilities can be carefully erased before it spreads too far, the branches fold back together and interfere once more, as though the split had never happened. For anything larger than a handful of particles, this is hopeless. The record smeared across too many things to ever gather back, so the separation is permanent in practice. But permanent in practice is not the same as absolute, and it means the line between one branch and the next is not a hard wall built into nature. It is a matter of how thoroughly the difference has leaked into the world, a matter of degree wearing the mask of a clean divide. There is a temptation to feel relieved by that, as though the ceiling tames the whole idea, and the relief would be premature. Because a new and worse problem is already visible in the word we have been leaning on, distinguishable. To count branches, you have to decide when two strands of the wave function count as truly different and when they are close enough to call the same. That decision is not handed to us by the equation. The wave function is one smooth object, and where you draw the lines that split it into this branch, and that branch depends on how you choose to look at it, on which features you treat as the ones that matter. The doubling we started with quietly assumed those lines were already drawn, that nature had cut the world into clean branches for us to count. Nothing in the physics ever did that. So the tally we set out to compute has slipped through our fingers in a second way, deeper than the first. The number of branches is bounded, yes, held under the ceiling of what one universe can hold. But beneath that ceiling, it is not even a fixed number, because it depends on a choice of how finely to carve a seamless whole, and different choices give different counts of worlds from the very same reality. The doubling was never counting something nature had already separated. It was counting the cuts we ourselves decided to make. If that unease feels familiar, it should. It is the same sickness we met in the cosmological multiverse, where the count of pockets dissolved into a question of where you chose to stop and how you chose to weigh. There, the ambiguity lived in a cutoff. Here it lives in a choice of what to treat as distinct. Two different multiverses, two different infinities, and the very same failure hiding underneath. That counting worlds keeps turning out to measure our choices rather than the world. Which leaves the sharpest question this branch of the journey can ask. If the number of worlds depends on how you choose to slice a single seamless wave function, then whose hand is on the knife? And is how many worlds a fact about the universe at all, or only a fact about us? To see whose hand is on the knife, you have to look at where the wave function truly lives, and it is not in ordinary space. It lives in an abstract mathematical space, a space of possibilities, and in that space the wave function is a single arrow pointing in some direction. To speak of branches, of separate worlds, you have to break that one arrow into parts, and to break it into parts, you must first choose a set of directions to break it along. Those directions are called a basis, and the quiet catastrophe is this. Nature does not hand you the basis. You choose it. A single example makes the whole problem visible, and it uses nothing more exotic than a beam of light. Take light polarized at a slant, at 45 degrees. Described along the slanted direction, it is one thing, a single clean state, one world. But the very same beam, described instead along the upright and sideways directions, is a blend of two, part upright and part sideways, a superposition, two worlds. Nothing about the light changed. Not one photon moved. All that changed was the set of directions you chose to describe it along, and with that choice alone the count went from 1 to 2. The number of worlds was never sitting in the light. It was sitting in your description of the light. The same slipperiness runs through everything, not just light. A particle sitting at one definite point looks like a single sharp world if you describe it by position. Describe that very same particle by its momentum instead, by how it is moving, and the one sharp point becomes a smooth spread over every possible speed at once, an endless superposition. Definite in one basis, a blur of countless possibilities in another, and both descriptions are of the identical, unchanged particle. Wherever you look, the number of things depends on the language you count in. So the count of branches is not a property of reality at all. It is a property of the questions we decide to ask of reality, the axes we lay down over a seamless whole before we start counting. Lay them one way, and there is one world. Lay them another, and there are 2 or 1,000. The wave function underneath does not flinch because we have not touched it. We have only chosen a grid, and then mistaken the lines of our own grid for seams in the world. There is a serious objection here, and it is the one that kept physicists working on this for decades. Surely, you might say, the world does not look like it could just as easily be described any old way. It looks classical, solid, made of definite objects in definite places, not a haze of arbitrary superpositions. And that is true, and the reason is decoherence, the same process from before. Decoherence does single out a special set of directions, the ones tied to position and to the ordinary properties that leak into the environment fastest, and it is why the world wears a classical face along those particular variables rather than others. So the basis is not entirely free. Nature does lean hard toward one family of descriptions. But lean is the honest word, and it is not enough to rescue a count. Decoherence tells you which variables become effectively classical. It does not hand you a sharp number of branches because the selection it makes is approximate, emergent, and continuous, never an exact partition into a clean integer of worlds, The branches it defines are fuzzy at their edges, forever splitting further, overlapping, never fully sealed, as we saw. Asking decoherence for the exact number of worlds is like asking exactly how many waves are on the ocean, or exactly how many separate clouds hang in the sky. The waves are real. The clouds are real. You can see them, point at them, be soaked or shaded by them. And still, there is no true integer that is the number of them, because the thing you are counting was never built out of sharply separate units in the first place. The instinct that there must be some definite number of worlds is very strong. It feels like a fact that is simply hidden from us, a figure we cannot reach but that surely exists, the way the number of grains of sand on a beach exists even if no one counts them. But the sand is made of separate grains. The wave function is not. It is one smooth, continuous object, and the worlds are our way of carving it into portions we can talk about, useful and even unavoidable, but not a set of pre-existing pieces waiting to be tallied. So what, in all of this, stays real and fixed, independent of how anyone chooses to describe it? Two things, and only two. The first is the one-wave function itself, the single arrow in the space of possibilities, evolving by its smooth rule. That is objective, the same for everyone. The second is the weight the wave function assigns to each possible outcome, a number that comes from squaring how much the arrow leans in that outcome's direction. That weight, and not the count of worlds, is what the theory predicts, and it is what every experiment has ever measured. This is the reframe that dissolves the question we started with. Trace back through the entire history of quantum mechanics, every prediction ever confirmed, every experiment ever run, and you will never once find the number of worlds appearing in any of it. What appears, always, is those weights, the probabilities of outcomes, and they are predicted with a precision unmatched anywhere in science. The count of branches has no such role. It was never measured, never predicted, never needed for a single result. It is baggage the cartoon added on top of a theory that was already complete without it. The physics is about how much weight each outcome carries, not about how many outcomes there are. Physicists who have worked hardest to make sense of the many worlds picture, David Wallace and Sean Carroll among them, are the first to insist that the exact number of branches is simply not part of the theory, that the whole content is the wave function and the weights it carries. The counting was never the physics. It was a story we told on the side, and a misleading one. And that turns the title of this entire journey, applied to the quantum multiverse, into something unexpected. How many worlds are there is not a question with a hidden answer we have failed to find. It is a question that quietly assumes the world comes in countable pieces, and the world, at this level, does not. The honest reply is not a number, large or small or infinite. It is that the quantity you are asking for was never well defined, and the theory works perfectly, predicts everything we see, without it. Those weights behave exactly like probabilities, and in a picture where every outcome truly happens, it is a real puzzle why they should. Why the weight given by squaring the arrow and not some other rule? Why should a version of you who keeps seeing the rare outcome be, in any meaningful sense, rarer, when that version is every bit as real as the rest? Serious people have serious proposals, and they do not yet agree, and this remains one of the live wounds of the whole subject. The proposals are ingenious and unfinished. Some try to show that any rational version of you, deciding how to bet before a measurement, is forced to weigh outcomes by exactly that squaring rule, on pain of contradiction. Others argue that a symmetry deep in the entangled state fixes the weights uniquely, leaving no freedom for any other rule. Each is elegant, each has committed critics, and none has won the field. So the one piece of this multiverse that is truly real, the weights, is also the piece we understand least. Still, one door has opened even as another closed. We assumed, this whole time, that if how many has an answer, that answer is a plain number or a plain endlessness. But mathematics has long known that infinity is not a single thing. There are infinities of different sizes, some strictly, provably larger than others. And if the honest answer to how many keeps refusing to be an ordinary number, perhaps we have been reaching for the wrong kind of quantity entirely, and the right question is not how many, but how large an infinity. The man who first took infinity seriously as a thing you could measure was Georg Cantor, and his starting move was so simple it looks like a trick. How do you compare two collections when both are endless and neither can be counted to the finish? You do not count them. You pair them. If you can match every member of one collection to exactly one member of the other, with nothing left unpaired on either side, then the two are the same size, whatever size means for something infinite. That single rule, pairing instead of counting, immediately does something that offends common sense. Take the whole numbers, 1, 2, 3, and on, and take just the even ones. There seem to have to be fewer evens since half the numbers are missing. But pair them anyway, 1 with 2, 2 with 4, 3 with 6, each number to its double, and the pairing is perfect. Every number matched, every even claimed, none left over anywhere. By Cantor's rule, then, there are exactly as many even numbers as numbers altogether. The part is the same size as the whole. Stranger still, the same works for the fractions, all of them, the entire dense thicket of ratios you can build. They too can be lined up and paired off with the plain counting numbers, one by one, with none escaping. The way you do it rewards seeing, because it feels impossible. Arrange every fraction in a vast grid, numerators along one edge, denominators along the other, so that every fraction sits somewhere in the mesh. Then, instead of trying to read the grid row by row, which would trap you forever in the first row, walk it in diagonal zigzags, back and forth across the corners, sweeping outward. That single winding path reaches every fraction in the entire infinite grid and lets you number them, first, second, third, with none missed and none skipped. All of these endless collections turn out to be the same single size of infinity, the smallest one, which Cantor named Aleph Null. So far, infinity looks like it comes in only one flavor, vast and uniform. Everything endless being endless in the same way. Cantor's great shock was to prove that this is false. Some infinities are strictly, provably larger than others, too large to be paired with the counting numbers no matter how cleverly you try. And the proof he gave is one of the most beautiful arguments in all of mathematics, simple enough to hold in your head, sharp enough to have changed what we think reality can contain. It runs like this. Consider every number between 0 and 1, written as an endless decimal, and suppose someone claims to have listed them all, a first, a second, a third, marching down the page forever, every such number somewhere on the list. Cantor shows the claim must be a lie by building a number that cannot possibly be on it. He walks down the diagonal of the list, taking the first digit of the first number, the second digit of the second, the third of the third, and so on. And he changes each one. Wherever the diagonal shows a 5, he writes a 6. Wherever it shows anything else, he writes a 5, building a brand new decimal digit by digit. Now ask where this new number could sit on the supposedly complete list. It cannot be the first number, because it differs from it in the first digit. It cannot be the second, because it differs in the second digit. It differs from every single number on the list in at least one place, by construction. So it is nowhere on the list, and yet it is a perfectly good number between 0 and 1. The list was never complete. No list ever could be. What overflows the list is the endless, non-repeating decimals, the irrational numbers, things like the square root of 2 or the ratio around a circle. The counting numbers and even all the fractions are, in a sense, rare islands. The vast, dense ocean between them is made of these unlistable decimals, and it is they that make the reals a larger infinity than anything you could ever line up in a queue. That is the whole proof, and its consequence is enormous. The numbers on the continuous line, the reals, cannot be paired with the counting numbers. There are too many of them. They form a strictly larger infinity, one we call the continuum, an endlessness that dwarfs the endlessness of the counting numbers, even though both go on forever. And Cantor found this was only the first step up an endless staircase. The collection of all possible groupings of any set is always strictly larger than the set itself, so that from any infinity you can build a bigger one, and from that a bigger one still, a tower of infinities climbing forever with no top floor anywhere. Now bring this staircase to the universes we have been counting, because it sorts them at last. The pockets of the first two multiverses, the endless regions of infinite space and the endless bubbles of eternal inflation are countable. You can list them, one region after another, one bubble after the next, in principle assigning each a place in an endless queue. However many there are, they sit at Aleph Null, the smallest infinity, the same rung as the plain counting numbers. But the quantum multiverse, and any space where a physical quantity can vary smoothly across a continuous range, lives higher up. A continuous range of possibilities cannot be listed, for the same reason the reals cannot. It is the larger infinity, the continuum. And this yields a ranking that should stop you cold. The quantum multiverse woven through this very room, if its worlds are counted as points in a continuous state, is a strictly larger infinity than all the pockets of infinite space and eternal inflation put together. The endless bubbles across all of creation are merely countable, Aleph Null. The worlds layered over your own bed tonight are the continuum, a heavier infinity than every far-off universe combined. The larger multiverse is not the distant one. It is the near one. So the honest answer to how many, when it can be given at all, is not a number but a place on Cantor's staircase, and the different multiverses stand on different steps. The landscape of string theory sits at a curious spot on that staircase. Counted as the discrete list of distinct foldings, it is finite, the 10 to the 500 from before, not even an infinity at all. But if the constants it sets could vary smoothly instead of in fixed steps, the space of possible laws would leap straight to the continuum. Whether a multiverse is finite, countable, or uncountable can hinge on nothing more than whether its dial clicks or turns. There is a strange comfort in that, after so much collapse. The question did not vanish entirely. It changed shape, from how many into how large an infinity, and in that new shape mathematics can begin to answer it, sorting the endless into ranks, countable here, continuum there, a real distinction with a real proof behind it. For the first time in several chapters, the tools do not simply break in our hands. A natural question sits right in front of us. Is there an infinity in between? Larger than the counting numbers but smaller than the continuum? A middle rung on the staircase? Cantor believed there was none and spent his later years unable to prove it. And in the 20th century, the matter was settled in the most unsettling way imaginable. Kurt Gödel and later Paul Cohen proved, together, that the question cannot be answered from the standard rules of mathematics at all. You may assume a middle infinity exists, or assume it does not, and either way the mathematics stays perfectly consistent, with no contradiction to catch you. The tools of the infinite, having sorted so much, reach a question they are built to be silent on. So the highest tier of counting we have reached still runs, in the end, into a wall inside mathematics itself, which forces one last, vertiginous question, the one that will carry us to the strangest level of all. If mathematics has its own infinities, its own limits, its own truths, it cannot decide. And if certain physicists have come to suspect that mathematics is not merely our description of reality but reality itself, then counting universes becomes counting mathematical structures. So, how many of those are there, and can the thing that has done all our counting for us tonight even count itself? The idea waiting at the top of this ladder is the boldest one anyone has seriously proposed, and it belongs mostly to a single physicist, Max Tegmark. It starts from something every scientist has felt, but few try to explain. Mathematics describes the world with a precision that has no right to be so perfect. The paths of planets, the behavior of light, the structure of the atom, all of it falls out of equations, again and again, far too well for comfort. The physicist Eugene Wigner gave this its lasting name more than 60 years ago, calling it the unreasonable effectiveness of mathematics, a gift we neither earn nor understand. Most people file that under a useful mystery and move on. Tegmark refused to move on. His move is to ask what the difference really is between a physical thing and its mathematical description. We usually assume the equation is one thing and the reality it describes is another, that the world is made of some physical stuff which the mathematics merely captures. But when you try to say what that stuff is, apart from its mathematical properties, apart from how it behaves and relates and measures, you find you cannot say anything at all. Strip away every mathematical property of a particle, its mass, its charge, its position, its relations, and nothing is left in your hand. So Tegmark takes the daring step. If a physical object is nothing over and above its mathematical structure, then perhaps the structure is the object, and no extra ingredient is needed to make it real. There is no separate fire that must be breathed into the equations to give them a world. The equations, if they hold together, are already a world. It helps to see how little a mathematical rule needs in order to become a world. There is a famous toy, a grid of squares that switch on and off by one plain rule about how many neighbors each has, and nothing more. That single rule, followed faithfully, gives rise to gliders that travel, structures that copy themselves, patterns that compute, whole intricate histories unfolding out of a definition you could write on a napkin. No one adds anything as it runs. The richness was already inside the rule, waiting. Tegmark asks you to take that seriously, and to imagine rules elaborate enough that the patterns inside them wake up and wonder where they are. Follow that thought where it leads, and it opens into the widest multiverse of all. If our universe is real because it is a consistent mathematical structure, then what is special about ours? Nothing, on this view. Every mathematical structure that hangs together without contradiction is a universe, as real as this one, existing in the only sense the word can now carry. To exist stops meaning something mysterious and starts meaning something plain. To exist is to be free of contradiction. A structure that does not contradict itself is a world, whether or not anyone is ever inside it to look around. The natural protest is to ask why, then, we find ourselves in this structure, with these particular laws, rather than some barren one. The answer is the same selection we have leaned on before, now raised to its most abstract form. Only structures rich enough to contain their own observers, patterns intricate enough to hold something that thinks and notices, can ever be experienced from within. The empty, simple structures are just as real, but no one is home in them to remark on it. We find ourselves in a structure complex enough to grow minds, because a mind is the only place from which any structure is ever seen. Here the counting suffers its final and most complete collapse, and it happens in two blows. The first comes straight from the mathematics of the infinite. There is no such thing as the set of all mathematical structures. For the same reason there is no set of all sets, a fact proved long ago. Such a collection is too large to be a set at all, too large to be assigned any size, even an infinite one. It does not sit high on Cantor's staircase. It sits off the staircase entirely, past the point where the word "how many" still means anything. The ultimate multiverse cannot be counted, not because it is endless, but because the collection of everything in it is not a well-formed thing to ask the size of. The second blow comes from Gödel. Suppose you tried to be modest and merely to list the consistent structures, checking each for contradiction and keeping the ones that survive. You cannot build that machine. Gödel and those who followed him proved that consistency in any system rich enough to contain ordinary arithmetic cannot in general be checked by any fixed procedure, and that no such system can even prove its own freedom from contradiction. The dream of a sieve that sorts all structures into the sound and the broken is not merely hard. It is impossible in principle, forbidden by the deepest results we have about the limits of reasoning itself. And there is a quiet elegance in how Gödel reached that limit, because his method was Cantor's method. He turned a system's own statements back on themselves, along a diagonal of self-reference, building a truth the system could describe but never prove, exactly as Cantor built a number his list could never contain. The same trick that ranked the infinities is the one that fences off what any system can know of itself. Restrict your attention to the structures that can be fully captured by a finite description, a finite recipe an idealized computer could follow, the computable ones. How many of those are there? Only countably many, the smallest infinity, aleph null. Because every finite description is just a finite string of symbols, and the finite strings can be listed, one after another, exactly the way Cantor listed the counting numbers. So, if you demand that a universe be describable by a finite rule, the grandest multiverse ever imagined collapses down to the lowest rung on the whole staircase, no larger than the plain numbers you learned as a child. That is a strange place to arrive. The most extravagant proposal in all of physics, the claim that every possible mathematics is a living world, answers our question with either no number at all, because the collection is too vast to be a set, or with the very smallest infinity there is, if we insist the worlds be describable. The two ends of Cantor's staircase, the bottom rung and the region beyond the top, and nothing ordinary in between. The plain count we wanted at the start of the night, a number you could say out loud, is nowhere on this level, and never could have been. I have to be as plain as I can about what kind of claim this is, because it is not like the others. The mathematical universe is the most speculative idea we have touched, and it sits at the very border where physics fades into philosophy. It makes no prediction anyone has found a way to test, and to many working physicists, that alone places it outside science and into metaphysics, a poem about reality rather than a theory of it. Its defenders answer that it is only the honest endpoint of taking seriously how thoroughly mathematical the world has turned out to be, and that dismissing it is a failure of nerve. Both sides have a real case, and no experiment stands ready to decide between them. And the old sickness returns here in its worst form. Even granting that every structure exists, to say what we should expect to observe you would need to weigh the structures, to say which kinds of worlds are common and which are rare among all of them. But there is no way to spread a measure over a collection too large to be a set, no fair way to weigh what cannot even be gathered into one place. The measure problem that broke the cosmological count and shadowed the quantum one returns at the top of the ladder more hopeless than ever. And that, finally, is the thread that ties every level together and pulls it tight. Whether we counted regions, or bubbles, or branches, or structures, the count kept dissolving into infinity, into ambiguity, into questions mathematics forbids us to answer. Through all of it, one demand has gone unmet, the plainest demand a skeptic can make. Show me. Not the argument, not the elegance, but the evidence. Is there a single measurement, one photograph of the sky, one flicker in a detector, that could ever reach out and touch even one of these other universes and turn all of this reasoning into something the eye can confirm? The quantum branches are sealed from us by decoherence, each blind and deaf to the rest, with no signal able to pass between them, ever. The mathematical structures lie beyond any telescope by their very nature, since there is no light that travels from one abstract world to another. Even the copies in infinite space sit hopelessly past our horizon, too far for any photon to have crossed in the age of the cosmos. 4 grand ideas, and 3 of them offer the eye nothing at all. But one of them is different, and it is the multiverse of eternal inflation, the endless bubbles. That one, alone among the 4, makes a mark that a real detector might find, and the reason traces back to how the bubbles form. Recall that our universe is one pocket that stopped inflating, a bubble nucleated in the churning sea, its wall racing outward at nearly the speed of light. Now suppose that early in its life, while it was still young and small, another bubble nucleated close by, and its wall came racing toward ours. The two would have touched. They would have collided. A collision like that does not pass without a trace. When another bubble strikes ours in those first instants, it disturbs the young universe on one side, dumping energy along the surface where the two walls met. Then, inflation, still running, takes that disturbance and stretches it enormous, the same way it stretched everything else, smearing a local bruise across a vast swath of what would become our sky. The imprint it leaves is not a random speckle. It is geometric, a disk, a perfectly circular patch on the sky, warmer or cooler than its surroundings, with a particular way the temperature slides from its center to a sharp edge. A collision has a shape, and the shape is a signature, unlike the ordinary random spots that pepper the microwave background everywhere. The shape even carries information about the collision that made it. How wide the disk spans on the sky, how sharply its temperature falls at the rim, how strong the difference runs from edge to center. All of it depends on how large the other bubble was and how hard it struck. A scar, if we found one, would not merely announce that another universe exists. It would let us read something about that universe off the geometry of the mark it left, a message pressed into our sky by a world we could never visit. So there is a real prediction here, and it can be hunted. Somewhere in the full map of the ancient light, if a neighboring bubble once struck ours, there should sit one of these circular scars, a round disk with a telltale profile, waiting to be found. And we have gone looking. Teams have taken the sharpest full-sky maps of the microwave background, the ones built over years of patient observation, and combed them with algorithms designed to catch exactly this circular signature, ignoring the random noise and flagging any true disk. The result, told plainly, is the honest kind of disappointment. A handful of candidate features turned up, spots that teased the pattern. None of them survived. Every one proved consistent with chance, an ordinary fluctuation dressed up to look like a scar, with no collision confirmed anywhere on the sky. There is one anomaly that keeps this from being a clean nothing, and it deserves a fair hearing. In one part of the southern sky sits a region called the cold spot, a stretch of the microwave background colder and larger than the simple theory comfortably expects. It has been floated, more than once, as a possible bruise from another universe, the very scar we have been hunting. But the more sober explanations have not been dislodged. It may be a rare but not impossible fluke of the ordinary randomness, the kind of oddity you expect somewhere when you scan a whole sky. Or it may be the mark of an enormous, mostly empty region of space between us and it, chilling the light that passes through. The cold spot is a real curiosity, and it is not evidence of another universe. It is a reminder of how badly we want one, and how carefully we have to hold that wanting. There is a second observational frontier, aimed not at the bubbles themselves, but at the machine that makes them. If inflation truly happened, it should have shaken space so violently that it sent out ripples in the fabric of the cosmos, primordial gravitational waves, and those would leave a faint, curled pattern twisted into the polarization of the ancient light. Finding that pattern would be powerful evidence for the very engine that spawns the endless bubbles. One team announced a detection back in 2014, and for a few weeks it seemed the case was made, before a careful reanalysis traced the signal to dust in our own galaxy. The hunt goes on, more sensitive each year, and the curl has not yet been found. Now, the deepest point of this whole search, the one that completes the hard truth we have been circling. The test is one-sided. If we ever did find a clear collision scar, a circular disk with the right profile, confirmed beyond chance, it would be extraordinary evidence that another universe brushed against ours, close to a smoking gun. A detection would speak loudly. But the absence of one says almost nothing. Finding no scar does not refute the endless bubbles, because a collision only leaves a mark if a neighbor happened to nucleate near enough, early enough, and strike hard enough, and most bubbles never do. The other universes could be out there in their multitudes and simply never have touched us, leaving a sky as blank as if they did not exist. A search that can confirm but never deny can hand you a discovery, or it can hand you silence, and the silence proves nothing at all. The one-sidedness cuts to the oldest question about what makes an idea scientific at all. A theory earns its standing, many argue, by sticking its neck out, by forbidding something, so that a single observation could in principle prove it wrong. A claim that can be confirmed by a lucky detection but never falsified by any absence sits uneasily on that line. It is not empty, since a detection really could arrive and settle everything. But a proposal that only ever risks being right and never risks being wrong asks us to trust it in a way ordinary science is built to distrust. That asymmetry is the wall this entire night has been walking toward. For one of the four multiverses, there is a narrow, one-directional window, a scar we might find, but whose absence we cannot read. For the other three, there is no window at all, no photograph, no detector, no measurement even imaginable that could reach them. So the count of universes, the number we set out to find, may lie permanently beyond the one method science truly trusts. Not merely unanswered tonight, but unanswerable by observation, perhaps forever, for almost everything we have discussed. And yet, I want to be as fair in this direction as in the other, because it would be easy to hear all this as debunking, and that would be its own kind of error. These multiverses are not idle fantasies conjured from nothing. Every one of them is a consequence, followed faithfully, of a theory that stands on real evidence in its own domain. Inflation is supported by the flatness and the spots we measured. Quantum mechanics is the most tested theory in history. The multiverses are what those trusted theories seem to imply when you take them at their word past the edge of where we can check. That is a very different thing from a fairy tale, and a very different thing from a fact. It is a shadow cast by solid physics into a region the light of measurement cannot follow. So, observation, the court of last resort, returns a verdict of mostly silence, and one narrow window that has so far shown us nothing, which leaves a single question standing, the last tool in the box when measurement fails. If we cannot see which of these pictures is true, is there any other honest reason to prefer one over another? And there is one principle, old and sharp, that scientists reach for exactly when the evidence runs out, a rule about simplicity. It has a surprising thing to say here, because when you apply it carefully, it does not favor the lonely single universe you might expect. It may favor the crowd. The razor everyone reaches for is nearly 700 years old, sharpened by a medieval friar named William of Ockham, and it says something that sounds beyond argument. When two explanations both fit the facts, prefer the simpler one, the one that assumes less. And almost everyone assumes without pausing that this cuts against the multiverse. One universe is surely simpler than countless universes. Why conjure endless worlds when a single one will do? The trouble is that this reasoning hides an unexamined word, and the word is simpler. To wield the razor properly, you have to say what simple means, precisely enough to measure. And the sharpest definition mathematics has found is not about how many things a theory contains. It is about how long the theory takes to describe. The complexity of something is the length of the shortest complete recipe that specifies it, the briefest set of instructions from which the whole thing can be rebuilt with nothing left out. Short recipe, simple. Long recipe, complex. This is the measure worked out by Andrei Kolmogorov and others, and it turns the razor into something you can compute with rather than wave in the air. There is a formal engine behind this instinct. In the mathematics of ideal prediction, worked out by Ray Solomonoff, Every possible explanation is weighed by the length of its shortest description, with briefer theories counting for exponentially more. It is the razor made rigorous. The reason a short rule should beat a long one not as a matter of taste, but as something close to a theorem about what best predicts the unseen. And in that formal court, a theory that generates everything and selects nothing scores strikingly well, precisely because it spends no words at all on choosing. Now the fact that overturns the whole intuition, and it is easier to see with numbers than with universes. Imagine writing the shortest possible instruction to produce every whole number, 1, 2, 3, and on forever. It is almost nothing. Start at 1 and keep adding 1 without end. A recipe of a single line generates an infinite list. Now instead write the instruction to produce one particular number, a specific string of 1,000 random digits, and nothing else. There is no shortcut. To pin down that one number, your recipe has to spell out all 1,000 digits, because there is no pattern to lean on, no rule shorter than the number itself. Producing everything took one line. Producing one specific thing took 1,000. That is not a quirk of numbers. It is the deep asymmetry at the heart of the whole question. Specifying all of something is cheap, because you need no rule for choosing. Specifying one particular member out of everything is expensive, because you have to encode the choice, the address, the which one of all the possibilities, and that selection is where the information hides. The same holds for the digits of pi. A short recipe computes pi to any length you like, endlessly. But a specific random million-digit string, with no pattern in it, needs a recipe 1,000,000 digits long, because the only way to describe it is to state it. Now carry that blade to the universes. Consider the theory that says all the pockets exist, or all the branches, or every consistent structure. To specify it, you write down the underlying rules, inflation running on, quantum mechanics with no collapse, and then you stop. You add no selection. You do not have to say which pocket, which branch, which structure. They all exist, so the recipe needs no address, no choosing, and it can be remarkably short. Now consider the rival theory, the lonely one, that says only this single universe is real. It needs those same rules. And then it needs something more, a great deal more. It has to specify which universe, out of all the possibilities, is the real one. Our exact constants, our exact initial conditions, the particular seed from which this cosmos and no other was grown. And that specification, the which one, is enormous. Recall how much information that seed holds. The early universe was sprinkled with a specific pattern of tiny quantum ripples, the one's inflation stretched into every galaxy, and to single out our world you would have to specify that entire pattern, ripple by ripple, across the whole sky. That is a colossal recipe, close to the full information content of the cosmos itself. The theory that lets all patterns happen needs none of it, not one ripple specified, because it declines to choose. So the razor, taken at its sharpest, does something almost nobody expects. It does not plainly favor the single universe. The single universe carries hidden baggage, the long, detailed instruction for picking out this world and discarding all the rest, and that instruction can be vastly longer than the bare rules that simply let everything be. By the measure of description length, generating all of it can be simpler than generating exactly one of it and throwing the remainder away. The crowd, counterintuitively, can be the cheaper hypothesis. The many worlds picture keeps only the smooth equation and lets every outcome happen. The rival picture keeps the same equation and adds a second rule, the collapse, that fires at moments it cannot define, and picks one outcome and erases the rest. One of these theories has an extra rule bolted on. The other does not. By the razor that counts rules, the many worlds picture is the leaner of the two, and its extravagance, all those branches, is not a cost the razor recognizes, because branches are contents, not rules. And there is the mistake the common intuition was making all along, now visible. It confused two entirely different kinds of complexity. The complexity of the stuff, how much there is, how many worlds, how much matter, and the complexity of the theory, how long the rulebook runs. The multiverse has more stuff and a shorter rulebook. The single universe has less stuff and a longer rulebook, because it must include the rule that picks the one. The razor was never designed to shave away stuff. It shaves away rules, assumptions, the length of what you must state to get the theory going. Science has walked this exact road before, more than once, and each time it walked toward more. To explain how matter behaves, we accepted that a single teaspoon of water hides more than 1 trillion invisible atoms, a staggering multiplication of unseen things, because the rules that followed were so much simpler than treating matter as a smooth, continuous whole. To explain the faint smudges in the night sky, we accepted that our galaxy is one among hundreds of billions, an overwhelming crowd of unseen worlds, because one galaxy sitting alone demanded stranger rules than a universe full of them. Every time, positing more of what we could not see bought a simpler law, and every time, science took the trade. The multiverse asks us to make that same move once again, and its defenders say we have no principled reason to refuse it now. Not everyone agrees that description length is the right meaning of simple. There is an older instinct, that a theory filling reality with unimaginable numbers of unobservable things is extravagant, no matter how short its equations, that counting entities, not counting rules, is the honest measure of what a theory asks you to swallow. By that instinct, the razor still cuts hard against the crowd. There is a technical thorn as well, familiar in spirit by now. The shortest description of anything depends on the language you write it in, on which machine is doing the reading, and that reference choice shifts the lengths around. For most purposes, the ambiguity stays small, but it means even our sharpest measure of simplicity is not perfectly unique, and the same freedom of choice that haunted every count in this story leaves a faint fingerprint here too. And beneath all of it stands a humbler caution. Occam's razor is a preference, a habit that has often served science well, not a law of nature and no guarantee of truth. The universe is under no obligation to be simple, by any definition we choose, and using a rule of thumb to settle what exists reaches past what the rule of thumb can bear. So the tool we brought in to break the tie does not break it. It does something subtler and more honest. It reveals that even simplicity, the last court we appealed to, does not point cleanly at the lonely universe, and may quietly point the other way, and that which kind of simplicity should rule is itself unsettled. The razor cuts, but it cuts in more than one direction, and no one has shown which edge is the true one. Which brings us, stripped of measurement and stripped of any clean verdict from simplicity, to the only thing left to do. Lay it all out plainly, level by level, and ask what an honest person can say tonight about how many universes there are. We have walked a long way to earn the right to say plainly where each one really stands. The first multiverse, the endless copies in infinite space, is the one that asks the least of us. It needs no new physics, no exotic ingredient, only that ordinary flat space runs on without end. And half of what it needs, we have measured. Space is flat, to the limit of our instruments, exactly as this multiverse requires. But the other half, that space is not merely vast but truly infinite. We have not measured, and may never be able to, since no view from inside a finite horizon can prove the outside goes on forever. So its count, a countable infinity of copies, each of us repeated without end, stands on one leg we have checked and one we have only assumed. The tamest idea, resting on the one thing we cannot confirm. Move up a level, to the endless bubbles of eternal inflation, and the ground grows firmer at the root and softer at the reach. Inflation itself has real support, having called the flatness and the pattern of the ancient spots correctly before we saw them. But the leap from inflation to eternal inflation, the machine that never stops, is an extrapolation, and the string landscape that gives its bubbles their 10 to the 500 flavors has never been confirmed by a single measurement. Worse, the count itself broke in our hands, because with infinitely many bubbles, no honest probability can be defined, and the question of how many, or how likely, lost its footing entirely. One narrow window remained, the scar of a bubble collision, and we searched the sky for it and found nothing. The third multiverse, the quantum branches, rests on the sturdiest foundation of all, the most tested theory in the history of science, taken simply at its word, with no collapse bolted on. It is no fringe notion, and some of the most careful minds in physics hold it as the plainest reading of what we already know. And yet its count is not a number at all. The branches cannot be tallied, because how finely you carve the one-wave function into worlds is a choice you bring, not a fact the world hands you. What is real and fixed there is the wave function and the weights it assigns, and the weights, the one solid thing, are also the piece we understand least, since no one has fully settled why they behave as probabilities when every outcome occurs. At the top sits the boldest claim of all, every mathematical structure made flesh, out where physics thins into philosophy. It makes no prediction anyone has learned to test, and its count either does not exist because the collection is too large to be a set, or shrinks to the smallest infinity there is if we demand the worlds be describable by finite rules. It is a serious idea, argued by serious people, and it is nowhere near established, and honest observers disagree on whether it is physics at all or a beautiful piece of metaphysics wearing the clothes of physics. There is a way of seeing these four that keeps them from feeling like rivals fighting over one throne. They stack. Each level sits above the last, so the real choice was never which multiverse, but how far up the ladder you are willing to climb before the ground gives way beneath you. Accept endless flat space, and you have the first. Accept the machine that fills it, and you have the second. Take quantum mechanics at its literal word, and you have the third. Believe that mathematics is not our map of reality, but its very substance, and you have the fourth. Each step asks for one more act of trust, and each takes you further from anything a telescope could ever check. Now stand back and look at the range of answers we have gathered, because the spread is the real result of this night. To the single question, how many universes are there? The honest replies run from one, through a countable infinity of copies, up to the larger infinity of the continuum, and on to no well-defined number at all. That is not a spread of magnitudes, a small number against a big one. It is a spread across kinds, from a finite thing you can hold, to infinities of different sizes, to a question that stops being well posed. The answer to how many multiverses there are is not a number we have failed to pin down. It is a family of very different kinds of answer, each true at its own level, none of them the plain figure we wanted when we began. And there may be a lesson hiding in how the counting kept failing, always in the same way. At every level, the obstacle was not that reality was too big, but that the question needed a choice we could not justify, a cutoff, a way of carving, a language, a measure. The same ghost walked through the cosmological count, the quantum count, and the mathematical one, wearing a different mask each time. Perhaps that recurrence is not a string of separate technical failures at all. Perhaps it is the world telling us that counting, the first tool we ever learned, quietly assumes a thing reality does not owe us, a set of clean, separate objects laid out and waiting to be tallied. A sharper measurement of the curvature of space could tighten or loosen the case for the first multiverse. A detection of the primordial gravitational waves from inflation would strengthen the engine behind the second, and a real collision scar would be close to a smoking gun. A breakthrough on the measure problem could give the second its probabilities back, and a convincing account of why the quantum weights are what they are could heal the deepest wound in the third. Even the steadiness of dark energy, whether it holds or slowly drifts, feeds back into which universes could ever host observers. These are not idle hopes. They are open problems that careful people are working now, and the honest answer a generation from tonight may not be the honest answer tonight. So what should a careful person do with all of this? Not swallow it whole, and not dismiss it whole, because both are lazy. The mature stance is graded, holding each level at its own weight. Trust the tested cores, inflation's successes, quantum mechanics' precision as the solid ground they are. Treat the extrapolations past the edge of measurement, the eternity, the landscape, the branches taken as literal worlds, the mathematical ensemble, as serious possibilities held at arm's length, believed lightly if at all, and never confused with things we have seen. And keep one more distinction close, that some of these worlds are forced on us and some are merely invited. The copies and the branches are not added to their theories by hand. They fall out whether we like it or not, once the theory is taken seriously, while the grand mathematical ensemble is a choice to believe something extra. A thing a theory forces on you deserves more of your trust than a thing you chose to assume. The honest position is not a verdict. It is a careful sorting of the confident from the plausible, from the merely conceivable. And through every level, across every argument, one number has never once wavered. Exactly one universe has ever been measured. 1. This one, the cosmos we can see, the only count the evidence has placed directly into our hands, without inference, without extrapolation, without a choice of measure or a leap past the horizon. Every other universe in this entire account, the copies, the bubbles, the branches, the structures, is something we reasoned our way to, never something we found. The one we can point to remains, stubbornly, alone in the ledger of things confirmed. It is a humbling place to land after so vast a journey, and a strangely steadying one, that the surest number in all of cosmology turns out to be the smallest one imaginable. There is one more counting machine we have not examined. It is not out past the horizon, or hidden in the landscape, or layered over the room. It sits behind your own eyes, in the 3 pounds of matter that has been doing all of tonight's counting, and it is about to run a computation of its own. One it performs every single night, on a scale that rivals the cosmos we have been measuring. The machine is your brain, and it runs on the same arithmetic we have used all night, only turned inward. Inside your skull sit about 86 billion neurons, and each one reaches out to thousands of others across tiny junctions called synapses, so that the connections between them number somewhere around 100 trillion, and by some counts closer to a quadrillion. That is the hardware. A web of junctions so dense that if you counted one every second, you would not finish before the sun burned out. Now ask the question this whole night has trained us to ask. How many distinct states can that web be in? Treat each connection, in the simplest picture, as something that can be strong or weak, on or off, and the number of possible configurations is 2 multiplied by itself once for every junction, 2 raised to a power with 14 or 15 zeros in it. That is a number built exactly the way we built the count of arrangements for a whole universe, a power of 2 over the pieces of a physical system, the same tool from the chapter on how many ways a cosmos can exist. I want to be honest about the size. That number is not as large as the universes. The count of ways to arrange a whole observable cosmos had an exponent with more than 100 zeros, and your brain's has only 14 or 15. Held against the universe, your mind is small. But hold it against anything human instead, and it stops being small in any way you can feel. The number of brain states available to you is so vast that every configuration every human mind has ever passed through, across all the people who have ever lived, all their waking and dreaming, is a single grain against a desert of what one brain could in principle become. And the deeper point is not the size at all. It is that the mathematics is identical. Your brain is a space of possible states with a probability spread across them, some configurations likely, most vanishingly rare, exactly the shape of thing we tried and failed to count across the multiverses. A state space and a measure over it. That is what a mind is, in the language of physics, and it is the very same language we spoke about bubbles and branches and structures. Not a metaphor for it. The same mathematics, running at a different scale, in the warm dark a few inches behind your eyes. Think back to the deck of cards from early in the night. A single shuffle almost certainly produced an order that had never appeared before in human history, because the deck's 10 to the 68th arrangements so far outrun the number of shuffles anyone has ever made. Your brain is that deck, made monstrously larger. The particular pattern of firing running through you at this exact moment, the precise state of those 100 trillion junctions, is almost certainly a configuration that has never once occurred, in any brain, in the whole history of life. And it will not occur again. You are, at every instant, a point in that space visited once and then left behind forever. Which brings us to what is about to happen as you lie here. The brain does not switch off when you sleep. It changes which region of that enormous space it wanders through. Awake, your neurons fire in fast, intricate, desynchronized patterns, billions of them chattering in loose crosstalk, the state shifting moment to moment as the world pours in. As you drift down, that changes. The chatter gives way to something slower and grander, great rolling waves of activity that sweep across the whole cortex in unison, tens of thousands of neurons rising and falling together, a tide replacing a storm. The space your mind explores does not shrink so much as calm, its restless corners going quiet, its motion turning long and smooth. Recall the field that drove inflation, resting in a valley of its landscape. A brain has valleys too, stable patterns it tends to fall into and settle within, and sleep is in part the mind letting go of the high, effortful states of waking and rolling down into the deep, easy basins where it can rest. You are not being switched off. You are coming to rest in the lowest, calmest valleys your own vast landscape holds. And in that slower state, the brain does its quiet work, none of which requires you to be awake for it. It replays fragments of the day, running the day's patterns again in miniature, moving what mattered into longer keeping and letting the rest fade. The passages between its cells open, and a slow wash of fluid moves through the tissue, carrying off the debris that the day's thinking left behind. There is real machinery in that washing. In the deepest stretches of sleep, the brain cells draw in a little, widening the channels between them, and cerebrospinal fluid pulses through in slow waves, rinsing away the byproducts that accumulate whenever you think. And the descent into it comes in stages, not all at once. First, a light drift, where the world loosens its grip and the muscles ease. Then a slightly deeper stage, marked by little bursts of activity called spindles, brief flurries that seem to help thread the day's learning into lasting memory. Then the deep, slow waves themselves, the grandest and most restful rhythm the brain ever produces. The whole sequence repeats through the night in long cycles, each roughly an hour and a half, carrying you down and down again like slow breathing made of sleep itself. Right at the threshold, a small structure deep in the brain begins to close the gates. The thalamus, the hub through which nearly all your senses pass on their way to awareness, quiets its traffic, and the outside world, the sounds of the room, the weight of the blanket, the faint light at the edges, stops reaching all the way in. The signals still arrive at your ears and your skin, but the gatekeeper has begun to let fewer of them through, and the mind is left to its own slow tides, sealed gently away from the day. Later in the night, in the stretches when dreams come, the brain lights up again, nearly as active as waking, and wanders into configurations it would never assemble while you are awake and tethered to the world. Every one of those dream states is another unrepeated point in the vast space, a place your mind visits once, in the dark, and never returns to. A strange comfort hides in that, after all our talk of copies. Somewhere out along the endless shelf, if it exists, another version of you may be settling into sleep tonight in an identical room. But even setting that aside, even inside this one life, this exact state of your mind will never come again. The night you are about to have is unrepeatable, a configuration the universe assembles once and then lets go. Whatever the true count of worlds turns out to be, this particular descent into sleep is happening only here, only now, only once. There is something quietly astonishing in all of this, laid beside everything we have counted tonight. The same kind of mathematics that could not settle how many universes there are, the state spaces, the probabilities, the numbers too large to hold, is running right now, without strain, in the tissue behind your face. And it does not stop to count anything. It does not need to know how many states it could be in, or how many dreams it might have had, or which configuration is likely and which is rare. It simply moves from one state to the next, generating tonight's particular pattern, a shape of mind that has never existed in the history of the universe and will not exist again after morning. So the last count of the night is the one you never have to make. Every number we chased across the cosmos came apart in our hands, into infinity, into ambiguity, into questions no measurement can reach. But the machine that did all the chasing asks nothing of the sort of itself. It runs the same deep mathematics the universe runs, effortlessly, silently, and it is winding down now, its storms softening into waves, its vast space of possibilities narrowing toward the long, slow rhythm of sleep. No formula is needed for what comes next. Only the quiet, and the tide of your own brain carrying you into it. After all of it, the copies and the bubbles, the branches and the structures, the infinities that would not resolve, and the questions that came apart in our hands, we are left with one number that held. 1. Not one as a disappointment, not one as a retreat from all that grandeur, but one as the single count the universe ever placed directly into our keeping. This cosmos, this room, this bed, and the quiet in it, and you, lying here at the center of the only universe anyone has ever confirmed. And you truly are at its center, in the one sense that carries any meaning. Remember that the sphere we can see reaches the same distance in every direction from wherever the observer happens to be. Which places you, right now, at the middle of a region 46 billion light-years across in every direction, not by any special importance, but by the plain geometry of how seeing works. The whole observable universe is arranged as a globe centered on this bed. Everyone's is. And tonight, yours is centered here. The physics we tracked across all those chapters did not stay out among the galaxies. He'd never left this room. The faint, leftover light from the universe's first moments, the glow we used again and again as our oldest evidence, is passing through you as you rest, thousands of those ancient photons crossing the space of your body every second, unfelt, on their way from the beginning of time to somewhere past the far wall. And some of that ancient light does not pass through at all. Some of it ends its long journey here, at you, photons that set out near the birth of the cosmos and traveled for 14 billion years to be stopped, at last, by your skin, by the blanket, by the soft closing of your eyes. You are where some of the oldest light in existence finally comes to rest. The strange energy of empty space, the one that took 120 decimal places to explain, is present in every gap between the particles of your own hand, gently, imperceptibly widening it. The quantum mathematics that may or may not be splitting the world is running in every atom of you, the same equation, the same weights, working away in the dark behind your closed eyes. You are not a spectator to any of this. You are made of it, and it is happening in you, now. Every atom of you traces back to the very first chapter of the night, to the one particle in 10 billion that outlived the great annihilation, when matter and antimatter met and canceled and left only the faintest sliver behind. You are that sliver, gathered and folded into a shape that can wonder about all the rest. The hand resting on the blanket, the heart keeping its slow time in your chest, all of it is the remainder the early universe could not quite erase, still here, still warm, 14 billion years on. That was the real shape of the night, if it had a shape. We set out to count the universes and found, instead, the exact place where counting stops working, and why. We learned that the plainest tool we own, the one we reach for before any other, quietly assumes the world is already cut into separate pieces waiting to be tallied, and that the deeper you go, the less the world obliges. The reward was never going to be a number you could say out loud. It was the view from the edge of what can be counted, and the small, steadying fact that when every grander count dissolves, the nearest one, the one you can reach out and touch, remains. And there is one last gentleness in how it all came out. Every count broke on the same thing, a choice we could not justify: where to stop, how to carve, what to weigh. All night the trouble was that counting demands a decision. But here, now, no decision is asked of you. Sleep is the one place that needs no measure, no cutoff, no choosing at all. You do not have to settle how many worlds there are in order to close your eyes. You only have to let the choosing go, along with everything else. So let the vast ones go, at least until morning. Let the copies stand at their unimaginable distances, unreachable and unproven. Let the bubbles keep forming in their endless sea, and the branches keep parting in their silent multitudes, and the mathematical worlds keep whatever kind of existence they have, out past every horizon we will ever measure. None of them asks anything of you tonight. None of them needs you to settle it. They will still be exactly as uncertain and exactly as beautiful when you wake. What is left is the one that is here. The weight of your own body against the bed. The slow, reliable rhythm of your breathing, which needs no theory and no proof, only the next breath, and then the one after that. The warmth of a single room in a single universe, the only one the evidence has ever handed us, holding you exactly where you are. And one is not so small a thing to be left holding. Everything you have ever seen, everyone you have ever loved, every morning you remember, and everyone still to come, all of it fits inside this single confirmed world, with room to spare. Whatever else may or may not be out there, past the horizon or layered over the room, nothing you have ever needed has been anywhere but here. I want to thank you, sincerely, for spending this long night here, for following all of it this far, through the enormous numbers and the honest uncertainties, all the way down to the quiet. It means a great deal to me that you stayed. There is nothing left to count now, and nothing left to solve. The one universe we are sure of is this one, and it is holding you gently, and it will keep turning while you rest. So let your thoughts go soft, and let the numbers drift, and let yourself sink into the calm, easy valleys we spoke of, down into the deep, slow waves. Sleep well. Rest easy in the one world we know is real. And good night.